A telescope aimed at nothing and found everything. James Webb pointed its mirror at a patch of empty sky smaller than a grain of sand held at arm's length. What appeared on the screens changed astronomy forever. The telescope revealed galaxies that formed when the universe was barely 300 million years old. Massive galaxies. Bright galaxies. Galaxies packed with billions of stars when there wasn't enough time for a single star to form. Everything scientists believed about cosmic dawn was wrong. If you're ready to see what's hiding in the ancient universe, please take a moment to like the video and subscribe. I'm also always curious to know where in the world and at what time you're joining me tonight. And now, settle in. Light left these galaxies 13.4 billion years ago. It traveled through expanding space across almost the entire history of the universe. The photons finally reached James Webb's Golden Mirror in 2023. What those photons revealed contradicts every model of how galaxies form. The universe is 13.8 billion years old. These galaxies existed when only 3% of that time had passed. If the universe's entire history was compressed into 1 year, these galaxies formed on January 11th. We are looking at cosmic infancy. James Webb launched on Christmas Day 2021. Scientists expected discoveries. They got a revolution. Within 6 months of activation, the telescope aimed at regions of sky that appeared empty to every previous instrument. What filled the images made veteran astronomers question decades of research. Galaxies swarmed across every frame. Big galaxies. Bright galaxies. Galaxies that had no business existing when the universe was barely born. The predictions said small and dim. Reality delivered massive and brilliant. Every theory about galaxy formation assumed a slow process. First, tiny clumps of stars would gather in the darkness. Over hundreds of millions of years, these dwarfs would collide and merge. Eventually, after countless collisions, galaxies like the Milky Way would emerge. The math worked perfectly, the timeline made sense, everything fit. James Webb looked back 13 billion years and found the timeline was fiction. Massive galaxies already lived and thrived when the cosmos was only 500 million years old. Galaxies containing billions of stars. When theoretical models said such structures needed billions of years to assemble. Imagine a human infant born with a doctorate degree and a retirement account. The comparison barely captures how wrong this feels to physics. Joel Leisure studies galaxies at Penn State. When he analyzed the first Webb images, his words were blunt. It calls the whole picture of early galaxy formation into question. This was not minor confusion. The foundation shook. The telescope operates in infrared. Human eyes see visible light, Webb sees heat. This matters because ancient light stretches during its billion-year journey to Earth. What started as visible light arrives as infrared radiation. The farther away something sits, the more its light stretches. Webb was designed to catch these ancient photons. And catch them it did. Thousands of data points flooded in. Each one confirmed the impossible. Galaxies filled the infant universe like cities fill modern Earth. Dense, organized, mature. The cosmic nursery looked more like a cosmic metropolis. Scientists checked the instruments. Calibration errors could explain strange readings. They recalibrated, ran diagnostics, checked again. The readings stayed consistent. The galaxies remained impossible. Some tried alternate explanations. Perhaps these were not galaxies at all. Maybe something else masqueraded as mature stellar cities. That hope lasted until spectroscopy confirmed what the images showed. These were real galaxies, real stars, real structure, existing when they should not exist. The discovery happened across multiple surveys: JWST, CEERS, GLASS, Cosmos Webb. Each program aimed Webb at different patches of sky. Each program found the same thing: ancient galaxies that broke the rules. One galaxy designated JADESGSZ 130 formed roughly 325 million years after the Big Bang. Another, JWST existed at 350 million years. These were not small, faint smudges. These were massive systems actively forming stars at rates that should have been impossible. The redshift values told the story. When astronomers measure how much light has stretched, they assign a number called redshift. Higher numbers mean greater distances and earlier times. Galaxies with redshift values above 10 represent the first 500 million years of cosmic history. Before Webb, astronomers had found perhaps a dozen such objects. Webb found hundreds in its first year alone. The sheer number of early galaxies created a crisis in cosmology. Models predicted the infant universe should contain mostly small, dim proto-galaxies, structures still forming, still gathering mass, still learning to make stars efficiently. Webb showed a universe already filled with mature stellar cities. This is where the physics breaks down. Star formation takes time. Gas must cool, collapse, fragment into stellar nurseries. The first stars, made only of hydrogen and helium, lived fast and died young. Their deaths seeded space with heavier elements. Those elements allowed the next generation of stars to form more efficiently. This process, repeated over and over, eventually built the galaxies we see today, or so the theory went. The timeline required billions of years. Early galaxies should have been small and inefficient, struggling to convert gas into stars. Webb found galaxies converting gas into stars at rates matching or exceeding modern spiral galaxies. Galaxies working at peak efficiency when they should have been fumbling through trial and error. One possible explanation involves dark matter, the invisible substance that outweighs visible matter 5-1. Dark matter creates gravitational wells, where normal matter collects. Perhaps dark matter halos in the early universe were denser than models predicted. Denser halos would pull matter together faster, accelerating galaxy formation. But even that explanation struggles with the observations. The galaxies Webb found are too massive, too quickly. Even with optimistic dark matter models, the timescales do not add up. Something fundamental is missing from our understanding. Some astronomers proposed that the first stars were more massive than expected, monster stars hundreds of times more massive than the Sunday. These titans would have burned through their fuel in mere millions of years, but they would have produced elements and energy at extraordinary rates. Their deaths in spectacular supernovae would have enriched space and triggered rapid star formation in surrounding gas. Evidence for these stellar monsters comes from chemical signatures in distant galaxies. Ratios of carbon to oxygen, nitrogen to carbon, that suggest extremely massive stars dominated early stellar populations. But even this does not fully explain what Webb sees. The telescope found galaxies with stellar masses exceeding 10 billion times the mass of the Sunday existing, when the universe was less than 500 million years old. To assemble that much mass requires either incredibly efficient star formation or a head start. We do not understand. One galaxy, designated CEERS 93316, initially appeared to have a redshift of 16.7. That would place it at just 235 million years after the Big Bang. Follow-up observations revised the redshift down to 4.9. Much closer, but still remarkably distant. The initial misidentification revealed how difficult these measurements can be. Light from the early universe arrives distorted, reddened, faint. Distinguishing a galaxy at redshift 16 from one at redshift 5 requires careful analysis. But even with revised distances, the fundamental problem remains. Galaxies exist earlier and larger than models predict. Webb continues to find them. Each new survey reveals more impossible objects. The telescope's near-infrared camera, NIRCam, captures images across multiple wavelength bands. By comparing how bright a galaxy appears in different infrared colors, astronomers can estimate its distance. Distant galaxies appear bright in redder wavelengths and dim or invisible in bluer wavelengths. This photometric redshift provides a quick estimate before follow-up spectroscopy confirms the distance. Spectroscopy splits light into its component wavelengths, revealing the galaxy's chemical composition and precise redshift. The instrument aboard Webb, NIRSpec, can observe multiple galaxies simultaneously using a microshutter array. Tiny shutters open to let light from specific galaxies through while blocking everything else. This allows efficient spectroscopic surveys of dozens of targets at once. The spectra show emission lines from hydrogen, oxygen, carbon, the same elements that make up stars today, but shifted dramatically toward the red end of the spectrum. Some lines shifted so far they move out of the visible range entirely, appearing only in infrared, where Webb can detect them. One emission line, Lyman alpha, marks neutral hydrogen. In nearby galaxies, this line appears in the ultraviolet. In the most distant galaxies Webb observes, Lyman alpha shifts into the near-infrared, moving more than a factor of 10 in wavelength. The amount of shift directly measures how much the universe has expanded since the light was emitted. This is what makes Webb revolutionary. Hubble could see some of these early galaxies, barely, as faint red smudges at the edge of its sensitivity. Webb sees them clearly, in detail, with enough light to measure their properties. The difference between knowing something exists and understanding what it is. The data revealed another surprise. Many early galaxies show evidence of already having experienced multiple generations of star formation. Older, redder stars mixed with young, blue stars. This means these galaxies did not just form recently. They had been building stars for potentially hundreds of millions of years before Webb observed them. That pushes the problem even earlier. If a galaxy observed at 500 million years after the Big Bang already contains old stars, when did those stars form? At 300 million years? 200 million years? How early can galaxies actually start assembling? Theoretical models now scramble to match observations. Some invoke extremely efficient star formation in the first dark matter halos. Others suggest the first stars formed earlier than previously thought, perhaps when the universe was only 100 million years old. A few radical proposals even question whether our understanding of cosmic expansion is correct. The cosmic microwave background, the afterglow of the Big Bang, provides independent constraints on the universe's age and expansion history. Those measurements agree with other cosmological observations. The universe is 13.8 billion years old. Expansion follows the patterns general relativity predicts. The problem is not with cosmology. The problem is with galaxy formation. Something about how gas cools and collapses and ignites into stars in the early universe works differently than models assumed. Perhaps magnetic fields played a larger role. Perhaps turbulence in the primordial gas helped accelerate collapse. Perhaps dark matter interacts with normal matter in ways not yet understood. James Webb continues to gather data. Each observation adds to the puzzle. Some galaxies appear disk-shaped, already showing rotational structure. Others appear irregular, chaotic, still in the process of assembly. A few show signs of interactions, early galaxies already colliding and merging despite the universe's youth. One survey, the Cosmos Webb program, covers nearly 1 square degree of sky. For reference, the full moon covers about half a square degree. Cosmos Webb peers deep into a relatively large area, searching for both extremely distant galaxies and rare objects at intermediate distances. The survey has already identified thousands of galaxy candidates across cosmic time. The preliminary results show galaxies at nearly every epoch of cosmic history, from the present day back to the first few 100 million years. The galaxy population evolves, but not in the simple, linear way models predicted. There are jumps, gaps, periods of rapid evolution, followed by apparent stasis. At redshift 8, roughly 600 million years after the Big Bang, the universe contained far more massive galaxies than models predicted. At redshift 10, 500 million years, the discrepancy grows worse. At redshift 12, 400 million years, the observations and predictions barely overlap. Some of the galaxies show active supermassive black holes at their centers, quasars powered by black holes containing millions or billions of solar masses. These black holes should not exist yet either. Growing a billion solar mass black hole requires time, either continuous feeding over hundreds of millions of years or some rapid growth mechanism not yet understood. One proposal suggests the first black holes formed directly from collapsing gas clouds without going through a stellar phase. Instead of a star forming, exploding, and leaving behind a stellar mass black hole that slowly grows. Perhaps some regions collapse directly into black holes weighing thousands or even millions of solar masses from the start. These seed black holes could then grow to supermassive scales more quickly. Evidence for this mechanism remains tentative. The conditions required for direct collapse are extreme. The gas must be hot enough to resist fragmenting into stars, but cool enough to actually collapse under its own gravity. A narrow window of temperatures and densities. Whether such conditions existed in the early universe is still debated. But Webb keeps finding supermassive black holes in the early universe. Active galactic nuclei at redshift 8, 9, 10. Black holes that somehow assembled when the universe was less than 5% of its current age. Each discovery tightens the constraints on formation mechanisms. The telescope's mid-infrared instrument, MIRI, adds another dimension to these observations. MIRI sees even longer wavelengths than NIRCam, detecting light from warm dust heated by stars and active black holes. In nearby galaxies, this dust emission traces star formation. In distant galaxies, the dust emission gets redshifted into MIRI's wavelength range, allowing astronomers to measure star formation rates in the early universe. The rates are staggering. Some early galaxies form hundreds of solar masses worth of stars per year. For comparison, the Milky Way currently forms about 2 solar masses per year. These early galaxies work 50 to 100 times faster, despite having less raw material available. Where does all that gas come from? Simulations show that gas flows along dark matter filaments, streams of matter connecting the cosmic web. Galaxies sit at the intersections of these filaments, constantly fed by inflowing gas. In the early universe, this feeding should have been particularly efficient. The universe was denser, filaments were thicker, gas fractions were higher. But the observations still exceed simulation predictions. The early galaxies form stars too efficiently for their available gas supply. Either the gas is more efficiently converted into stars, or there is more gas than models assume. Neither explanation is fully satisfying. Another possibility involves feedback. When stars form and die, they release energy back into their surroundings. Supernovae explosions, stellar winds, radiation pressure. This energy heats surrounding gas, potentially blowing it out of the galaxy entirely. Feedback regulates star formation, preventing galaxies from converting all their gas into stars at once. In the early universe, feedback might have worked differently. Perhaps the first supernovae were less effective at disrupting star formation. Perhaps the deeper gravitational wells of dark matter halos held onto gas more tightly. Perhaps radiation from the first stars had different effects on surrounding material. The metallicity of early galaxies provides clues. Metallicity measures the abundance of elements heavier than helium. Stars produce these heavy elements through nuclear fusion. When stars die, they release these elements into space. Subsequent generations of stars incorporate these heavy elements. Low metallicity indicates a young stellar population with few previous generations. High metallicity indicates an old population enriched by many cycles of star formation and death. Webb can measure metallicity through spectroscopy, identifying emission lines from oxygen, carbon, nitrogen. Some early galaxies show surprisingly high metallicity. oxygen abundances reaching 20 or 30% of solar values. This suggests rapid enrichment, many massive stars living and dying quickly, churning through nuclear fusion and producing heavy elements at extraordinary rates. This chemical evolution should take time. Models predict that galaxies at redshift 10 should have metallicities only a few % of solar values. Some galaxies match these predictions. Others exceed them by factors of 3 or 5. The scatter in metallicity at any given redshift is larger than models anticipated. This scatter hints at diversity in galaxy formation pathways. Not all early galaxies evolved the same way. Some assembled mass quickly, ignited intense star formation, and enriched rapidly. Others grew more gradually, building mass over longer timescales. The mix of pathways produced the diversity Webb observes. Understanding this diversity requires larger samples. Webb's first year of observations provided hundreds of early galaxy candidates. Ongoing programs aim for thousands. With thousands of galaxies spanning cosmic dawn, astronomers can measure distributions, track evolution, identify rare objects, and test models statistically, rather than through individual case studies. The JADES program, Joint JWST and HST Extragalactic Deep Survey, combines Webb observations with archival Hubble data. By observing the same regions of sky with both telescopes, astronomers can compare how galaxies appear in visible and infrared light. Hubble shows the rest frame ultraviolet, light emitted by hot young stars. Webb shows the rest frame optical and near-infrared, light from older stars and dust. Together, the two telescopes reveal galaxy structure and stellar populations. Hubble's high resolution shows where star formation concentrates. Webb's infrared sensitivity shows total stellar mass and dust content. The combination paints a complete picture. Many early galaxies are compact. Stellar masses equivalent to the Milky Way, compressed into regions only a few thousand light-year across. For comparison, the Milky Way's disk spans 100,000 light-year. These compact galaxies pack enormous mass into tiny volumes, resulting in extreme stellar densities. Why early galaxies are so compact remains unclear. Perhaps they have not yet accumulated the extended disks seen in later galaxies. Perhaps gas has not yet settled into rotating structures. Perhaps mergers between compact systems dominate early assembly, and extended disks only form later. Some early galaxies show disk-like structures. Rotation curves measured from emission lines reveal organized motion. Gas orbiting a central mass concentration. These rotating disks suggest that even in the early universe, some galaxies achieved stable configurations. Others appear irregular and chaotic. Clumpy star formations scattered throughout asymmetric structures. These galaxies might be caught in the act of assembly, multiple components merging and settling into a coherent system. The morphological diversity at early times was unexpected. Models predicted that massive, well-organized galaxies would not appear until later cosmic epochs. Webb shows that even at redshift 10, the galaxy population includes both chaotic and organized systems. Gravitational lensing amplifies some of the most distant galaxies. When a massive foreground object, like a galaxy cluster, sits between Earth and a distant background galaxy, the cluster's gravity bends the background galaxy's light. This magnification allows Webb to see galaxies that would otherwise be too faint. The lensing is not uniform. Different regions of the background galaxy get magnified by different amounts. The image appears distorted, stretched into arcs or multiple images. By modeling the lensing, astronomers can reconstruct the background galaxy's true appearance and measure its properties. One lensed galaxy, designated SPT0615JD, appears triply imaged by a foreground cluster. Webb observes all three images, providing multiple views of the same galaxy and allowing detailed reconstruction. The analysis reveals a galaxy at redshift 10, with ongoing star formation and complex structure. Without lensing, this galaxy would be invisible even to Webb. Lensing effectively gives Webb a boost in sensitivity and resolution. The magnification factor can reach 10 or even 100 times for galaxies aligned perfectly behind dense cluster cores. This allows the study of galaxies that would otherwise remain beyond reach. But lensing also introduces complications. The magnification varies across the galaxy, distorting measurements of size and structure. The lensing model must be accurate to properly reconstruct the galaxy's properties. Uncertainties in the cluster's mass distribution translate to uncertainties in the background galaxy's measurements. Despite these complications, lensing remains a powerful tool. Planned observations will exploit lensing to push even deeper, searching for galaxies at redshift 15 or 20. If such galaxies exist, lensing might reveal them. The question of how early galaxies can form has no definitive answer yet. Webb is still gathering data, astronomers are still refining models, and the picture remains incomplete. But some patterns are emerging. The first stars likely formed between 100 and 200 million years after the Big Bang. These population 3 stars, made entirely of hydrogen and helium, lived fast and died young. Their supernovae seeded space with the first heavy elements, enabling the next generation of stars to form more efficiently. By 300 million years, the first small galaxies assembled. Dark matter halos reached masses sufficient to trap cooling gas. Star formation ignited in these halos, creating the first stellar systems. These proto-galaxies were not the massive systems Webb sees at redshift 10. They were smaller, simpler, less massive. Between 300 and 500 million years, rapid assembly occurred. Small proto-galaxies merged, pooling their mass. Gas streamed in along dark matter filaments, fueling intense star formation. Some systems grew quickly, reaching billions of solar masses. Others grew more slowly, remaining small and faint. By 500 million years, the galaxy population was diverse. Massive galaxies, dwarf galaxies, active star-forming systems, quiescent systems already exhausted of gas. The variety Webb observes reflects different formation histories and environments. This rapid assembly requires efficient processes. Gas cooling quickly, collapsing rapidly, igniting into stars at high rates. The early universe's higher density aided this efficiency. Gas was closer together, dark matter halos were denser, gravitational forces were stronger. But efficiency alone cannot explain the most massive systems. There must be additional factors. Perhaps feedback was less effective at suppressing star formation. Perhaps magnetic fields channeled gas more efficiently into dense regions. Perhaps turbulence in the primordial gas aided collapse rather than hindered it. Some theoretical models invoke primordial density fluctuations. The universe was not perfectly uniform after the Big Bang. Some regions were slightly denser than average, others slightly less dense. The denser regions collapsed earlier and formed structures sooner. If some regions were significantly denser than average, they could have formed massive galaxies very early. The cosmic microwave background maps these density fluctuations. The patterns of hot and cold spots reflect the distribution of matter 380,000 years after the Big Bang. Those patterns seeded the formation of galaxies billions of years later. By comparing galaxy distributions with microwave background fluctuations, astronomers can test whether primordial overdensities explain early massive galaxies. Preliminary analyses suggest that standard fluctuations cannot fully account for the most extreme early galaxies. The densest regions predicted by microwave background data are not dense enough to form billion solar mass galaxies by 500 million years. Something beyond standard density fluctuations is required. One possibility is non-standard inflation. Inflation is the period of rapid expansion that occurred in the first fraction of a second after the Big Bang. Different models of inflation predict different patterns of density fluctuations. Some models allow for larger fluctuations on small scales, creating denser regions that could collapse into massive galaxies earlier. Testing this requires comparing galaxy observations with increasingly sophisticated models. Webb's data provides the observations. Theorists provide the models. The iterative process of comparison and refinement gradually narrows the possibilities. Another approach involves simulating galaxy formation directly. Cosmological simulations start with the Big Bang, model the expansion of the universe, track the growth of density fluctuations, follow the collapse of dark matter halos, and simulate gas cooling, star formation, and feedback. Modern simulations include increasingly realistic physics, attempting to reproduce observed galaxy properties. The simulations that best match observations of nearby galaxies struggle to reproduce the early massive galaxies Webb finds. The same physics that works at late times fails at early times. This suggests that either the physics changes, the parameters need adjustment, or some process is missing from the simulations. Adjusting star formation efficiency helps, but does not fully solve the problem. Even with unrealistically high efficiency, converting every available atom of gas into stars, the most massive early galaxies remain difficult to produce. The raw material is simply not there in sufficient quantities early enough. Some simulations explore exotic scenarios. What if dark matter is not entirely cold? Warm dark matter would suppress small-scale structure but might enhance large-scale collapse, potentially producing massive galaxies earlier. What if dark matter self-interacts? Interactions could alter halo formation in ways that accelerate galaxy assembly. These scenarios remain speculative. The evidence for exotic dark matter properties is weak. Most data supports cold, non-interacting dark matter. Invoking exotic properties to explain early galaxies is a last resort, attempted only after conventional explanations fail. For now, the tension remains unresolved. Webb observes galaxies that should not exist. Models cannot yet explain them. The gap between observation and theory drives new research, new simulations, new observations. The telescope continues its mission. Each year brings deeper observations, larger samples, better statistics. The JWST Advanced Deep Extragalactic Survey, JDIS, will eventually observe for more than 500 hours in select deep fields. This investment of time delivers sensitivity unmatched by any other facility. With sufficient integration time, Webb can detect galaxies at redshift 15 or beyond. The first 250 million years of cosmic history. Galaxies forming when the universe was less than 2% of its current age. If such galaxies exist, Webb will find them, and if they do not exist, that is also informative. A lack of galaxies at the highest redshifts would indicate a hard limit on how early structure can form. It would constrain the timing of the first stars, the first black holes, the first starlight. Either outcome advances knowledge. Science progresses through both confirming expectations and discovering surprises. Webb has provided mostly surprises. Each surprise teaches something new about the universe's infancy. The implications extend beyond galaxy formation. Understanding when and how the first galaxies assembled informs models of cosmic reionization. Reionization is the process by which the first stars and galaxies ionized the neutral hydrogen filling the universe. This transformed the cosmos from opaque to transparent, allowing light to travel freely through intergalactic space. The timing and sources of reionization remain uncertain. Did stars and galaxies provide most of the ionizing radiation, or did black holes contribute significantly? Did reionization occur quickly or gradually? Did it proceed uniformly or in a patchy, uneven manner? Webb's observations of early galaxies help answer these questions. By measuring the number and brightness of galaxies at different redshifts, astronomers can estimate the total ultraviolet radiation they produced. This radiation ionized surrounding hydrogen, gradually clearing the fog. The current data suggests that galaxies alone can account for reionization, provided faint dwarf galaxies are included. These faint systems, just beyond Webb's detection limits, might outnumber bright galaxies significantly. Their combined light output could drive reionization without requiring significant contribution from black holes. But uncertainties remain. The fraction of ultraviolet photons that escape galaxies is poorly constrained. Some models assume 10% escape, others 20%, some as high as 50%. The escape fraction directly affects how efficiently galaxies ionize their surroundings. Webb can measure escape fractions in individual galaxies through spectroscopy. By comparing the strength of emission lines from ionized hydrogen inside the galaxy to the diffuse emission from hydrogen outside, astronomers infer what fraction of photons escape. Early measurements show a wide range of escape fractions, from nearly 0 to over 50%. This diversity complicates models. If some galaxies leak ultraviolet photons efficiently, while others do not, the average escape fraction depends on the mix of galaxy types. And that mix might evolve with time, changing the pace of reionization. The end of reionization occurred around redshift 6, roughly 1 billion years after the Big Bang. By that time, most hydrogen in the universe was ionized. The detailed history before that remains murky. Did reionization start at redshift 15, 12, 10? Did it proceed smoothly, or in bursts, corresponding to waves of star formation? Webb's observations at redshift 10 and beyond probe the era when reionization was underway. The galaxies discovered at these redshifts are the actors driving the process. Their properties, their numbers, their UV output collectively determine how reionization proceeded. One signature of reionization is the Lyman alpha forest. Neutral hydrogen absorbs Lyman alpha photons, creating absorption features in the spectra of distant quasars. As the universe reionizes, the amount of neutral hydrogen decreases, and the Lyman alpha forest evolves. By studying this absorption, astronomers trace the ionization state of the universe across cosmic time. The Lyman alpha forest appears fully developed by redshift 6, indicating reionization is complete. At higher redshifts, the forest becomes denser, more opaque, suggesting increasing neutral fractions. But the exact evolution is noisy and difficult to interpret. Different sightlines show different absorption patterns, reflecting the patchy nature of reionization. Webb cannot observe the Lyman alpha forest directly in most cases. That requires background quasars, which are rare at the highest redshifts. But Webb can detect the galaxies causing reionization and measure their properties, providing complementary information. The picture emerging from Webb's first 2 years of data shows a universe assembling structure earlier and more vigorously than models predicted. Galaxies appear massive and mature when they should be small and young. Star formation ignites at rates that should be impossible. Black holes grow to supermassive scales when they should barely exist. This is not a crisis for cosmology. The Big Bang model remains secure. The universe's age and expansion history are well established. The cosmic microwave background, distant supernovae, galaxy surveys all agree on the fundamental framework. The crisis is in the details. How gas turns into stars, how stars form galaxies, how galaxies evolve. These processes are more complex, more variable, more surprising than models assumed. And that is where progress happens, in confronting the gap between expectation and reality. James Webb provides the reality: crisp, detailed, precise observations of the early universe. Astronomers provide the models, adjusting parameters, testing scenarios, iterating toward explanations that match data. This process will take years. Webb's mission is planned for a decade or more. Each year brings more data, deeper observations, larger samples. Each year narrows the range of viable models. Each year brings science closer to understanding cosmic dawn. The question of why early galaxies are so massive has no simple answer. It likely involves multiple factors: efficient star formation, dense environments, rapid mergers, perhaps primordial density fluctuations larger than expected, perhaps dark matter halos assembling earlier than models predict, perhaps feedback working differently in the early universe. Disentangling these factors requires observations across multiple wavelengths, multiple surveys, multiple approaches. Webb leads this effort, but ground-based telescopes contribute as well. ALMA observes early galaxies in millimeter wavelengths, tracing cold gas and dust. The Atacama Large Millimeter Array can resolve the distribution of gas within early galaxies, showing where star formation occurs and how gas flows. Radio telescopes search for emission from neutral hydrogen in early galaxies. The Square Kilometer Array, currently under construction, will eventually map hydrogen across cosmic time, tracking how gas feeds galaxies and how star formation consumes that gas. Optical and near-infrared telescopes on the ground complement Webb with different capabilities. The extremely large telescope, when completed, will have a 39-meter mirror, far larger than Webb's 6.5-meter mirror. Ground-based telescopes suffer from atmospheric interference, but they can observe continuously, gathering data night after night. Together, this suite of facilities will map the early universe in unprecedented detail. Webb provides the census of early galaxies. ALMA provides gas measurements. Radio telescopes trace hydrogen. Optical telescopes follow up bright targets with high-resolution spectroscopy. The data will eventually reveal how galaxies actually formed in the early universe. Not through models and simulations, but through direct observation of the galaxies themselves. Their masses, their sizes, their star formation rates, their chemical abundances, their morphologies. All measured, catalogued, analyzed. From this census will emerge understanding. The processes that dominated early assembly, the timescales involved, the role of mergers, gas accretion, feedback, environment, the diversity of formation pathways and the factors driving that diversity. This understanding will ripple through astrophysics. Galaxy formation models will be revised. Cosmological simulations will be updated. Predictions for future observations will change. The field will advance, driven by Webb's discoveries. But even as understanding improves, mysteries will remain. The universe is complex. 13 billion years of evolution produce structures ranging from dwarf galaxies to galaxy clusters. No single model will explain everything. The goal is not perfect prediction, but robust understanding of the dominant processes. James Webb has already achieved something remarkable. It has shown that the early universe was more vibrant, more active, more surprising than anyone predicted. Galaxies assembled faster, stars formed earlier, structures emerged sooner. This does not overturn cosmology, it refines it. The Big Bang happened. The universe expanded and cooled. Atoms formed, matter clumped, stars ignited. That sequence is secure. The timing and efficiency of each step is what Webb is revising. And every revision brings new questions. If galaxies formed this early, when did the first stars actually ignite? If black holes grew this quickly, how did they form? If star formation was this efficient, what made it so? Each answer opens new questions. This is how science progresses. Not toward final answers, but toward deeper questions. Each layer of understanding reveals new complexity beneath. Webb will observe for as long as its fuel lasts and its instruments function. Current estimates suggest at least 10 years of operation, possibly longer. Over that time, the telescope will accumulate thousands of hours of observations, tens of thousands of galaxies, millions of data points. From that data will come understanding, not all at once, not in a single revelation, but gradually through the patient work of analysis, modeling, comparison, revision. Science is a process, and Webb is accelerating that process. The galaxies that should not exist are forcing astrophysics to confront its assumptions about star formation efficiency, about dark matter halo assembly, about gas cooling and accretion, about feedback and its effectiveness. Every assumption is now under scrutiny. Some will survive revision, some will not. The models that best match Webb's observations will guide future research. The models that fail will be discarded, their assumptions identified and corrected. This is the scientific method in action: observation, hypothesis, prediction, testing, revision. Webb provides the observations and tests. Astronomers provide the hypotheses and predictions. The iterative cycle continues. One thing is certain: the early universe was not the quiet, gradual nursery that models predicted. It was a factory, churning out galaxies at extraordinary rates. Massive galaxies, bright galaxies, complex galaxies, all appearing when they had no business existing. This factory operated on principles not yet fully understood. The physics was the same: gravity, thermodynamics, nuclear fusion. But the conditions were different: denser, hotter, more extreme. And in those conditions, galaxies assembled in ways that current models struggle to reproduce. Understanding those conditions is now a priority, not just for galaxy formation, but for cosmology as a whole. The early universe sets initial conditions for everything that follows. Get the early universe wrong, and every subsequent prediction is suspect. Webb is getting the early universe right, not through theory, but through observation. The telescope is showing astronomers what actually happened, not what models predicted should happen. And what actually happened is more extreme, more rapid, more surprising than anyone imagined. The massive galaxies Webb discovered at redshift 10, 12, 13 are real. Their light has traveled across 13 billion years of space to reach us. They existed when the universe was an infant, and their existence demands explanation. That explanation will come, not today, not this year, but eventually. Through the combined efforts of observers, theorists, simulators, and instrumentalists. Through thousands of hours of telescope time and millions of hours of analysis. Through trial and error, success and failure, insight and revision. This is the process of discovery. And James Webb has accelerated it dramatically. The telescope has delivered more early galaxy discoveries in 2 years than all previous telescopes combined over decades. The data is still being analyzed, the surprises are still being catalogued, the implications are still being explored. But the impact is already clear. Everything astronomers thought they knew about early galaxy formation requires revision. The timeline needs adjustment, the efficiency parameters need recalibration, the physical models need refinement. This is not failure, this is progress. Science advances most rapidly when confronted with data that contradicts expectations. Webb has provided exactly that kind of data. And the field is responding, racing to develop models that match observations. The race is far from over. New data arrives monthly. Each observing program delivers new galaxies, new measurements, new constraints. The models evolve in response, incorporating new physics, testing new scenarios. Somewhere in this process, understanding will crystallize. The confusion will resolve into clarity. The pieces will fit together. And the early universe will make sense again. Not as the simple nursery of models, but as the complex, dynamic, surprising place that Webb reveals. We are witnessing the birth of that understanding. The data that will enable it is being collected now. The analysis that will reveal it is underway now. The theories that will explain it are being developed now. This is an extraordinary moment in astronomy. A time when observations outpace theory, when discoveries exceed predictions, when the universe reveals itself faster than science can explain it. This moment will not last forever. Eventually theory will catch up, models will match data, understanding will crystallize. But for now, we live in the age of discovery. And James Webb is the instrument driving that discovery, revealing galaxies that should not exist, challenging everything astronomers thought they knew, and demanding better explanations. The universe does not care what our models predict. It exists as it exists, following physical laws we are still learning to understand. James Webb is teaching us those laws, one impossible galaxy at a time. And what we are learning is humbling. The universe assembled structure earlier, faster, more efficiently than our best models predicted. The first galaxies were not tentative experiments. They were fully formed systems, massive and bright and complex, existing when the cosmos had barely begun. This tells us something profound. The universe is capable of more than we imagine. The processes that create galaxies can operate at speeds and efficiencies we have not yet reproduced in simulations. The early universe was not a slow, gradual process. It was explosive, rapid, transformative. Life itself depends on those early galaxies. They produced the first heavy elements, the carbon and oxygen and iron that eventually allowed planets and life to form. They reionized the universe, clearing the fog and allowing light to travel. They set in motion the processes that would eventually produce the Milky Way, the Sun, the Earth. Understanding those galaxies is understanding our own origins. The atoms in our bodies were forged in stars that formed in early galaxies. The physics that governs our existence traces back to processes operating when the universe was 500 million years old. James Webb is revealing that history, not as abstract theory but as concrete observation. Real galaxies, measured and catalogued and analyzed, their properties recorded, their evolution traced, their impact quantified. This is the gift of astronomy. The ability to observe the past directly by capturing ancient light. Every photon Webb detects is a messenger from cosmic dawn, and those messengers bring news of a universe more amazing than we imagined. The galaxies that should not exist are teaching us that our imaginations were too limited. We thought we understood how structure forms. We thought we had the timeline figured out. We thought the early universe would be simple and predictable. We were wrong, and that is wonderful, because being wrong means there is more to learn, more to discover, more to understand. The universe is larger, more complex, more surprising than our models captured. James Webb is showing us that larger, more complex, more surprising universe. And in doing so, the telescope is expanding not just our knowledge, but our sense of what is possible. Galaxies can form earlier than we thought. Stars can assemble faster than we predicted. Structure can emerge from chaos more efficiently than we modeled. These lessons extend beyond astrophysics. They speak to the capacity of nature to organize, to create complexity, to build structure. From quantum fields to galaxies, the universe exhibits an astonishing ability to generate order from randomness. The early galaxies are examples of this capacity. Within a few 100 million years of the Big Bang, gravity had already sculpted gas into coherent systems. Star formation had already ignited. Chemical enrichment had already begun. The machinery of cosmic evolution was already running at full speed. This machinery operates according to physical law: gravity, thermodynamics, quantum mechanics, general relativity. The same laws that govern phenomena in laboratories on Earth. Nothing mysterious or magical. Just physics, operating in extreme conditions on vast scales. But the outcome is extraordinary. From a nearly uniform plasma emerged structure. From randomness emerged organization. From simplicity emerged complexity. And it happened fast, on timescales cosmology had underestimated. James Webb is documenting this emergence. The telescope's images and spectra are snapshots of the process in action. Galaxies caught in various stages of assembly, from chaotic clumps of stars to organized rotating disks. Each snapshot reveals something about how the process works. And the process is still not fully understood. The data Webb provides will fuel research for years, as astronomers work to explain what the telescope observed. Models will be proposed, tested, refined. Simulations will be run, parameters adjusted, physics included or excluded. Through this process, understanding will grow. Not perfectly, not completely, but substantially. Enough to make sense of the main features Webb observed. Enough to predict what future telescopes might find. Enough to connect early galaxy formation to the broader story of cosmic evolution. That story is still being written. James Webb is adding crucial chapters, filling in details about the universe's youth that were previously missing. Each observation adds a sentence, a paragraph, a page. The complete story will take decades to write. Webb will contribute its observations. Future telescopes will add theirs. Theorists will weave the data into coherent narratives, and gradually the picture will become clear. But even as clarity emerges, wonder will remain. Because the universe is not just a puzzle to be solved. It is a reality to be experienced. And experiencing the early universe through Webb's eyes is humbling and exhilarating. We are matter organized in a way that allows it to study matter. Atoms contemplating atoms. Galaxies observing galaxies. The universe reflecting on itself through conscious beings who build telescopes and ponder distant light. James Webb has given us a new mirror for that reflection. The telescope shows us the universe as it was, revealing epochs and structures hidden from previous generations. And in showing us the past, Webb illuminates the present and hints at the future. The galaxies that should not exist are part of our history. They are ancestors of the Milky Way, distant relatives in the cosmic family tree. Understanding them is understanding where we came from, how we got here, what processes shaped the universe into its current state. And that understanding is worth pursuing. Not for practical applications or technological benefits, though those may come, but for the sake of knowledge itself, for the human drive to comprehend our place in the cosmos, for the satisfaction of answering deep questions about existence. James Webb has posed new questions even as it answered old ones. The telescope has shown that early galaxies are more massive than expected, but why remains unclear. The data has revealed rapid star formation, but the mechanism is uncertain. The observations have demonstrated that models are incomplete, but the missing physics is still unknown. These are good questions, difficult questions, questions that will drive research for years, and in pursuing answers, astronomers will learn not just about galaxies, but about the fundamental workings of the universe. This is the value of discovery. Not just the facts themselves, but the process they initiate, the questions they raise, the research they inspire, the understanding they eventually produce. James Webb has delivered discoveries that will fuel astrophysics for a generation. The impossible galaxies are only the beginning. Each observing program reveals new phenomena, new objects, new mysteries. The telescope is a gift that keeps giving, a source of data and inspiration that will outlast its operational lifetime, because the data will remain. Even after Webb stops observing, the archive will continue to yield insights. New analysis techniques will extract information the original observers missed. New theoretical frameworks will reinterpret old data in new ways. The telescope's legacy will extend far beyond its active mission. But for now, Webb is still operating, still observing, still discovering. The impossible galaxies are being catalogued and studied. The data is being analyzed and modeled. The mysteries are being confronted and gradually unraveled. And we get to witness this process, not as distant observers but as participants. Each new Webb result is shared publicly. Each discovery is announced. Each paper is published. The process of science happens in real time, visible to anyone interested enough to follow. This transparency is astronomy's gift to the world. The universe belongs to everyone. The discoveries made with telescopes funded by public resources are shared with everyone. James Webb's observations are available to all, inspiring wonder and curiosity across cultures and generations. The galaxies that should not exist are part of humanity's shared heritage. They existed before the Earth formed. They shone when the universe was young. Their light has traveled across billions of years to reach us, carrying information about cosmic dawn. And now we can decode that information. Thanks to James Webb, thanks to infrared astronomy, thanks to decades of technological development and scientific preparation, we can observe galaxies at the edge of existence and measure their properties and learn their stories. This is an extraordinary capability, a triumph of human ingenuity and collaboration. Thousands of people across dozens of countries worked for decades to make Webb possible. Engineers, scientists, administrators, technicians, all contributing pieces to a project that now reveals the universe's deepest secrets. The impossible galaxies are the reward for that effort, the validation of that investment, the justification for every hour spent designing, building, testing, launching, calibrating. Because the discoveries are real, the galaxies exist, the data is solid, and the implications are profound. Not just for astrophysics, but for our understanding of existence itself. The universe is older than the Earth by a factor of 3. It is larger than the observable region by unknown amounts. It contains more stars than humans can easily comprehend. And it assembled structure earlier than we predicted. It formed galaxies faster than we modeled. It created complexity on timescales we underestimated. This is what James Webb has shown us. This is the reality the telescope reveals. A reality more impressive than our models, more dynamic than our simulations, more surprising than our theories. A reality that demands better explanations and rewards our curiosity with deeper understanding. James Webb is teaching us humility. The universe does not conform to our expectations. It operates according to its own rules, indifferent to our models and predictions. Our job is to observe carefully, measure precisely, and adjust our understanding to match reality. This is what science does. It holds theories accountable to data. It revises models when observations contradict them. It pursues truth through evidence rather than assumption. And James Webb is providing the evidence that drives this process. The impossible galaxies exist. The data is clear. The measurements are precise. The challenge now is explaining them. And that explanation will come through hard work, creativity, and persistence. Through testing hypotheses and discarding failures. Through building better models and running smarter simulations. The process is underway. Astronomers around the world are working on this problem. Theorists are developing new models. Simulators are testing new physics. Observers are gathering more data. The collective effort of the scientific community is focused on understanding what Webb revealed. And eventually that understanding will emerge. Not as a single breakthrough, but as gradual progress. Each paper will add a piece. Each simulation will test an idea. Each observation will constrain a parameter. And slowly the puzzle will come together. When it does, we will look back at this moment as a turning point. The moment when observations forced astrophysics to confront its assumptions about early galaxy formation. The moment when James Webb showed us that the universe is more capable than we imagined. This moment will be remembered. The impossible galaxies will be studied in textbooks. The discoveries will shape how future generations understand cosmic history. And the lesson will endure. The universe always has more to teach us than we expect. James Webb is the messenger delivering that lesson. The telescope looks into the ancient universe and shows us what really happened. Not what we thought happened, not what models predicted, but what actually occurred, captured in photons that traveled across cosmic time. Those photons tell a story of rapid assembly and efficient star formation, of massive structures emerging early, of a universe more dynamic and complex than theoretical frameworks anticipated. A story that is still being decoded, still being understood, still being integrated into the larger narrative of cosmic evolution. We are privileged to witness this story's unfolding, to live in an era when telescopes like Webb reveal the universe's deepest secrets, to have access to data showing galaxies at the edge of time, to participate in the process of discovery even as observers watching from the sidelines. The impossible galaxies are out there, frozen in ancient light, waiting to be understood. James Webb has found them. Astronomers are studying them. And slowly, through patience and insight, their secrets will be revealed. This is the promise of science, that mysteries can be solved, that questions can be answered, that the universe, despite its vastness and complexity, is ultimately comprehensible, not easily, not quickly, but eventually. James Webb has shown us what needs comprehending. The impossible galaxies that challenge our models and demand explanation. The early universe that assembled structure faster than predictions allowed. The cosmic dawn that was more vibrant than anyone expected. Understanding this will take time, but the journey is underway. Driven by curiosity, guided by evidence, sustained by the human desire to know. And at the end of that journey will be understanding. Deeper, richer, more complete than what we have now. The impossible galaxies will become possible. The mysteries will become knowledge. The surprises will become expected. And we will look back at this moment and recognize it for what it is. The beginning of a new chapter in our understanding of the cosmos. James Webb opened that chapter. The telescope revealed what previous instruments could not see. And in doing so, it transformed our view of the early universe from theoretical abstraction to observed reality. That reality is more amazing than fiction, more complex than models, more surprising than predictions, and it is ours to study, to understand, to marvel at. Because we live in an age when technology allows us to observe the universe's infancy. When light from cosmic dawn reaches our detectors. When impossibility becomes observation. The galaxies are real, the data is solid, the challenge is clear, and the opportunity is extraordinary. To witness science grappling with new data, revising old models, building new understanding. To see the process of discovery in action happening now, driven by James Webb's observations. This is what the telescope was built for. To push the boundaries of knowledge. To reveal what lies beyond current understanding. To show us a universe more wondrous than we imagined. And in the impossible galaxies, Webb has delivered exactly that. A glimpse of cosmic dawn that defies explanation and demands our attention. The universe is speaking, James Webb is listening. And we get to hear what it says. About the first galaxies, the first stars, the first light. About how structure emerged from chaos. About how quickly the cosmos organized itself into the majestic complexity we observe today. That message is still being deciphered, but the words are clear enough. The early universe was not quiet. Not slow, not simple. It was vigorous, rapid, complex. A cosmic crucible where galaxies formed at speeds we are still struggling to explain. Consider galaxy JWST at redshift 12.63. This system existed just 330 million years after the Big Bang. Spectroscopic analysis reveals it contains roughly 4 billion solar masses in stars. To assemble that much stellar mass in 330 million years requires converting gas into stars at rates exceeding 100 solar masses per year on average. For comparison, the Milky Way today forms about 2 solar masses per year. The efficiency required is staggering. Nearly every atom of available gas must find its way into stars. Feedback from supernovae and stellar winds must be ineffective at disrupting the process. The galaxy must be a perfect star formation machine, operating at theoretical maximum efficiency. But even maximum efficiency struggles to explain JWST. The raw materials simply were not abundant enough in the early universe. Baryonic matter, the normal matter that makes stars, constituted only about 16% of the total matter budget. The rest was dark matter, which does not form stars. If all the baryonic matter in a typical dark matter halo at redshift 12 collapsed into stars with perfect efficiency, you might produce a billion solar mass galaxy. Maybe 2 billion. Reaching 4 billion requires either exceptional halos with more baryonic matter than typical, or multiple halos merging and pooling their stars. Both scenarios are possible but statistically improbable. Finding one such galaxy is surprising. Finding dozens suggests that either the processes are not as improbable as models predict, or something fundamental about the early universe differs from assumptions. One proposal involves the initial mass function. This function describes the distribution of stellar masses at birth. In nearby galaxies, most stars are low mass, less than the Sun. High-mass stars are rare. This distribution affects how efficiently gas converts into long-lived stars versus short-lived massive stars. If the initial mass function in the early universe favored more massive stars, star formation would appear more luminous but less efficient at building long-term stellar mass. Massive stars burn bright and die young, converting much of their mass back into gas through stellar winds and supernovae. Only a fraction ends up in long-lived stellar remnants. But spectroscopic measurements of early galaxies suggest metallicities consistent with normal stellar populations, not heavily skewed toward massive stars. The chemical signatures do not support a dramatically different initial mass function. The stars forming in early galaxies seem similar in their mass distribution to stars forming today. This brings the mystery back to the fundamentals. How do you form billions of solar masses in stars when there is not enough time, not enough gas, and not enough efficiency, even with optimistic assumptions? Some researchers now question whether the stellar mass estimates are accurate. Measuring mass requires assumptions about stellar populations, star formation histories, and dust content. Different assumptions produce different mass estimates. Perhaps the early galaxies are less massive than initial analyses suggest. Follow-up observations aim to constrain these uncertainties. By measuring multiple emission lines, astronomers can better model the stellar populations. By observing in mid-infrared with MIRI, they can detect dust emission and correct for its effects. By obtaining deeper spectroscopy, they can identify faint features that reveal star formation history. These refinements might reduce the estimated masses by factors of 2 or 3. That would help ease the tension with models. But even reduced masses of 1 or 2 billion solar masses at redshift 12 remain challenging to explain. The fundamental problem persists at slightly less extreme levels. Galaxy CERS 2588 at redshift 11.6 shows a disk-like morphology. The galaxy appears elongated in Webb's images, suggesting a rotating structure rather than a spherical blob of stars. Follow-up spectroscopy confirms rotation, with one side approaching and one side receding as measured through Doppler shifts of emission lines. Disk galaxies require angular momentum. The gas must spin as it collapses, settling into a rotating configuration rather than falling directly to the center. Where does this angular momentum come from in the early universe? Tidal interactions with neighboring structures can impart angular momentum. As gas flows along dark matter filaments, gravitational interactions torque the material, causing it to spin. Simulations show that this process can produce rotating disks even in the early universe. But the time scale is important. Gas must flow in, acquire angular momentum, and settle into a stable disk. This takes time. Finding well-formed disks at redshift 11 suggests that the process works faster than simulations typically reproduce. The presence of disks also affects star formation. Disk galaxies tend to form stars more steadily over time compared to merger-driven starbursts. Steady star formation would help explain how early galaxies accumulate mass without requiring implausibly high peak star formation rates. If GHZ2 and similar galaxies grew through steady disk accretion rather than violent mergers, the average star formation rate over hundreds of millions of years might be high, but not impossibly so. The key is maintaining that rate over long enough timescales. This requires continuous gas supply. The galaxy must accrete gas from its surroundings faster than star formation consumes it. In the dense early universe, with abundant gas flowing along filaments, such continuous accretion is plausible. But observational evidence for this accretion is limited. Webb can see the galaxies themselves, but struggles to detect the diffuse gas flowing into them. The gas is too faint, too spread out, too cool to emit strong lines at the wavelengths Webb observes. Ground-based facilities like ALMA might eventually detect this gas through emission from carbon or oxygen. These elements, even in low abundances, produce detectable lines at millimeter wavelengths. Mapping the distribution of gas around early galaxies would reveal whether they are actively accreting from their surroundings. Another galaxy, Galaxies 13, was initially reported at redshift 13.2, placing it at 320 million years after the Big Bang. Subsequent spectroscopic follow-up revised the redshift down to 10.4, still distant but not record-breaking. The revision illustrates the difficulty of photometric redshift estimates. Without spectroscopy, astronomers estimate redshift by comparing a galaxy's brightness in different infrared filters. The shape of the spectral energy distribution indicates how much redshift has occurred. But dust, emission lines, and other factors can mimic or mask the signatures of high redshift. Spectroscopy removes this ambiguity by directly measuring emission or absorption lines. The wavelength shift of these features gives a precise redshift. But spectroscopy requires longer integration times, making it impractical to confirm every photometric candidate. As a result, the literature contains many photometric redshift estimates awaiting spectroscopic confirmation. Some will be confirmed at or near their estimated redshifts. Others will be revised down. A few might even be revised up. The revision of Galaxies 13 from redshift 13.2 to 10.4 did not eliminate the galaxy's scientific value. At redshift 10.4, it remains one of the most distant spectroscopically confirmed galaxies. Its properties still challenge models, just slightly less extremely than initially thought. This illustrates the iterative nature of discovery. Initial findings based on limited data generate excitement and motivate follow-up. Follow-up observations refine measurements and sometimes revise conclusions. The process gradually converges on accurate characterizations. James Webb enables this process by providing both survey depth and spectroscopic capability. The telescope can image large areas to find candidates, then point back at interesting targets for detailed spectroscopy. This combination of breadth and depth is unprecedented. Previous telescopes had to choose. Hubble provided deep imaging but limited infrared spectroscopy. Ground-based telescopes provided spectroscopy but struggled with faint infrared targets. Spitzer provided infrared imaging but lacked the resolution and sensitivity for detailed studies of distant galaxies. Webb combines all these capabilities: imaging and spectroscopy, near and mid-infrared, sensitivity and resolution. The result is a comprehensive view of the early universe impossible with previous facilities. Galaxy MAX 0647 JD sits behind a massive galaxy cluster that lenses and magnifies its light. The lensing boosts the galaxy's brightness by a factor of 8, bringing it within Webb's reach. Without lensing, the galaxy would be too faint to study in detail. The galaxy appears triply imaged by the cluster's gravity. 3 separate images of the same galaxy, distorted by gravitational bending, but recognizable as the same object. By modeling the lensing and combining information from all three images, astronomers reconstruct the galaxy's true properties. The analysis reveals a galaxy at redshift 10.7 undergoing a burst of star formation. The system contains perhaps 100 million solar masses in stars, modest by later standards, but significant for the early universe. The ongoing starburst is forming stars at a few solar masses per year. This rate is more modest than the extreme cases like GHC2. It represents a more typical early galaxy, one that does not break records, but illustrates the diversity of objects present at high redshift. Not every early galaxy was a massive outlier. Many were smaller systems, still in the process of building mass. These smaller galaxies might be the building blocks that eventually merge to form the massive galaxies. If 10 galaxies like MAX 0647 JD merged over a few 100 million years, the result could be a billion solar mass system, like those seen at slightly later times. This hierarchical assembly matches theoretical expectations. Small halos form first, hosting small galaxies. These halos and their galaxies merge, creating progressively larger systems. Over cosmic time, the galaxy population shifts from many small galaxies to fewer large galaxies. But the pace of this assembly in the early universe appears faster than simulations reproduce. The massive galaxies seen at redshift 10 require either unusually efficient merging or unusually massive seed galaxies. Either way, something about the early universe's assembly process exceeded theoretical predictions. Perhaps the dark matter halo mass function at high redshift is different from what simulations predict. If massive halos formed earlier or more abundantly than expected, they could host massive galaxies earlier. This would shift the entire assembly timeline forward without requiring changes to star formation physics. Testing this requires measuring the dark matter halo properties of high redshift galaxies. Galaxy clustering provides one probe. Galaxies in more massive halos tend to cluster more strongly with other galaxies. By measuring how early galaxies cluster, astronomers infer the typical halo masses. Webb's wide-area surveys will eventually enable such clustering measurements. With thousands of galaxies across large fields, statistical analyses can measure how they group together. Comparing these measurements to simulations will reveal whether halo masses match expectations or skew higher. Another probe involves gravitational lensing of background galaxies by foreground dark matter. This weak lensing signal is subtle but measurable with sufficient data. Future surveys combining Webb imaging with ground-based observations might detect weak lensing around massive early galaxies, directly measuring their halo masses. Galaxy JWST701QU at redshift 7.3 shows unusual spectroscopic features. The galaxy appears quiescent, meaning star formation has ceased or dropped to very low levels. Finding a quiescent galaxy at redshift 7 is unexpected. Quenching star formation requires removing or heating the gas supply. Supermassive black hole feedback can do this by injecting energy that drives gas out of the galaxy. Stellar feedback can also contribute through cumulative effects of supernovae and stellar winds, but these processes take time. Building a supermassive black hole massive enough to quench a galaxy requires millions of years of growth. Accumulating enough stellar feedback requires many generations of stars. Finding a quenched galaxy at redshift 7 implies that these processes operated quickly. The galaxy's stellar population appears old, with ages exceeding 500 million years. If true, stars began forming when the universe was less than 200 million years old. This pushes the epoch of first star formation even earlier than the massive star-forming galaxies suggest. It also raises questions about what triggered star formation so early and what subsequently quenched it. The galaxy must have formed, built up its stellar mass, exhausted its gas, and shut down star formation, all within the universe's first billion years. That is a complete life cycle compressed into a tenth of the time seen in nearby galaxies. Perhaps this galaxy represents an extreme outlier, a statistical fluke caught in an unusual evolutionary state. Or perhaps quenched galaxies were more common in the early universe than models predict, implying that feedback mechanisms were highly effective. Follow-up observations aim to confirm the quenched nature and refine the stellar age estimates. If confirmed, JWST Z701QU will become a touchstone for models of early quenching. Understanding how it formed and died will constrain galaxy evolution theories. The diversity of galaxies at high redshift is striking. Massive starbursts like GHZ2, rotating disks like CERS2, 588, lensed systems like MAX 0647JD, quenched galaxies like JWST-GSZ701QU. Each represents a different evolutionary pathway, a different configuration of gas, stars, and dark matter. This diversity implies that even in the early universe, galaxy formation was not a uniform process. Different environments, different initial conditions, different random events produced different outcomes. Some galaxies grew massive quickly, others grew steadily, some formed stars vigorously, others shut down early. Understanding this diversity is as important as understanding the average. The variety reveals the range of physical processes operating in the early universe. Each type of galaxy probes different aspects of star formation, feedback, accretion, and assembly. Webb's large samples enable statistical studies of this diversity. By cataloging hundreds or thousands of early galaxies, astronomers can measure distributions of mass, star formation rate, size, morphology, and other properties. These distributions constrain models more tightly than individual objects. A model that reproduces the average properties but misses the diversity is incomplete. The tails of the distribution, the rare objects, the extremes, all carry information about the physical processes. A complete model must explain not just typical galaxies but also the outliers. Galaxy HD1 at redshift 13.27 briefly held the distance record before subsequent discoveries pushed farther. Spectroscopic confirmation placed it at 324 million years after the Big Bang. The galaxy is bright in ultraviolet light, suggesting vigorous star formation or an active supermassive black hole. Distinguishing between these scenarios requires detailed spectroscopy. Stars and black holes produce different emission line ratios. Stars emit strong hydrogen and oxygen lines. Active black holes add high ionization lines like carbon IV and magnesium-2, plus a strong continuum from the accretion disk. Initial spectra of HD1 show hints of both stellar and AGN signatures. The galaxy might host both intense star formation and a growing black hole. This combination is common in later galaxies, but finding it at redshift 13 is noteworthy. If HD1 contains an active supermassive black hole, the black hole must have grown to at least 1 million solar masses by 324 million years after the Big Bang. That requires rapid growth from smaller seeds, either stellar mass black holes from the first stars or more massive seeds from direct collapse. The debate over black hole seed formation remains unresolved. Stellar mass seeds face a challenge called the Eddington limit. Black holes can only accrete so fast before radiation pressure from the accretion disk blows away incoming material. To grow a stellar mass black hole to supermassive scales in a few 100 million years requires near-continuous accretion at the Eddington limit. This is possible, but requires special circumstances. The black hole must have a steady supply of gas and minimal disruption from feedback or galaxy mergers. Whether enough black holes experience such favorable conditions to explain the population of early supermassive black holes is uncertain. Direct collapse seeds would start with masses of 10,000 to 100,000 solar masses. Growing to supermassive scales from these seeds is easier, requiring less time and less continuous accretion. But the conditions for direct collapse are restrictive. Only rare regions of the early universe might have met the requirements. Webb's discovery of multiple active black holes at high redshift will eventually reveal which formation pathway dominated. If most early supermassive black holes have masses too large to have grown from stellar seeds, direct collapse becomes more attractive. If the masses are consistent with stellar seed growth, that pathway remains viable. The answer matters for understanding structure formation. Black holes and galaxies co-evolve. Supermassive black holes influence their host galaxies through feedback. Understanding when and how black holes formed constrains galaxy formation models. Galaxy CEERS 1749 at redshift 8.5 shows an unusual spectral feature interpreted as a possible population 3 signature. Population 3 stars are the hypothetical first generation of stars, made entirely of hydrogen and helium with no heavy elements. These stars have never been directly observed. They would have formed in the first dark matter halos to collapse, igniting nuclear fusion and ending the cosmic dark ages. Their lifetimes were short, perhaps only a few million years for the most massive examples. By the time galaxies assembled, population 3 stars had already died. But their deaths would have enriched surrounding gas with the first heavy elements. Detecting these elements in early galaxies reveals that POP3 stars existed. Direct detection of active POP3 stars would require observing the first halos at redshift 15 or higher, which remains beyond current capabilities. The feature in CEERS 1749 spectrum might instead reflect unusual ionization conditions or contamination from foreground sources. Follow-up observations will attempt to confirm or refute the population 3 interpretation. If confirmed, CEERS 1749 would become the closest we have come to observing the universe's first stellar generation. Understanding population 3 stars matters for cosmic chemical enrichment. These stars produce the first carbon, oxygen, iron, and other elements. Without them, subsequent star formation would have remained inefficient. The first galaxies depended on POP3 enrichment to build their stellar populations. The mass range of population 3 stars is debated. Some models predict mostly massive stars, 100 to 300 solar masses, living fast and dying in violent pair instability supernovae. Others allow for a broader mass range, including smaller stars that might survive to the present day as ancient fossils in the Milky Way's halo. No confirmed POP3 survivors have been identified in the Milky Way. The most metal-poor stars discovered contain trace amounts of heavy elements, suggesting they formed from gas already enriched by earlier generations. True population 3 stars with exactly 0 heavy elements remain elusive. Webb's observations of early galaxies provide indirect evidence for POP3 stars through the chemical signatures they left behind. By measuring metallicities in the most distant galaxies, astronomers trace the buildup of heavy elements. Extrapolating back to even earlier times suggests when the first enrichment occurred. That timing constrains the epoch of POP3 formation. If galaxies at redshift 12 already show significant metallicity, POP3 stars must have formed and died earlier, perhaps at redshift 15 or 20. If metallicities at redshift 12 are very low, POP3 formation might have extended until later times. Current data shows a range of metallicities at high redshift, from near 0 to 20% solar. This diversity suggests that POP3 enrichment was patchy, affecting some regions earlier than others. The first supernovae enriched their immediate surroundings, but took time to spread elements throughout the universe. Galaxy SMACS 0723Z11 appears in Webb's first deep field image, released in July 2022. The galaxy's light traveled for more than 13 billion years before reaching the telescope. It appears as a small red smudge, barely distinguishable from noise without careful analysis. Spectroscopic follow-up confirmed the redshift and revealed ongoing star formation. The galaxy converts gas into stars at roughly 10 solar masses per year, modest but significant for its small size. The stellar mass is only 100 million solar masses, less than many globular clusters in the Milky Way. But this small galaxy plays a crucial role. Systems like SMACS 0723Z11 might have been the dominant galaxy population at high redshift. While massive galaxies like GHZ2 grab headlines, dwarf galaxies likely outnumbered them by factors of 10 or 100. These dwarf galaxies collectively contributed more to cosmic reionization than massive galaxies. Their combined ultraviolet output, summed over countless systems, ionized the hydrogen-filling space. Understanding reionization requires understanding the dwarf galaxy population. Webb's sensitivity extends deep enough to detect these dwarfs at high redshift. Previous telescopes struggled to see anything below 1 billion solar masses beyond redshift 6. Webb routinely detects 100 million solar mass galaxies at redshift 10 and beyond. This capability is transforming reionization studies. Instead of inferring the dwarf galaxy population from models and extrapolations, astronomers now measure it directly. The number of dwarfs, their star formation rates, their ultraviolet output, all constrained by observations. Early results suggest that dwarf galaxies are more abundant at high redshift than models predicted. The luminosity function, which describes how many galaxies exist at each brightness level, appears steeper than anticipated. More faint galaxies exist relative to bright galaxies than models expected. This steepening has major implications. If confirmed, it means dwarf galaxies dominated the ultraviolet background that drove reionization. Massive galaxies played a supporting role rather than leading. The picture of reionization shifts from top-down, driven by rare bright objects, to bottom-up, driven by abundant faint objects. Testing this requires measuring the dwarf galaxy luminosity function across multiple redshifts. Webb's ongoing surveys will accumulate sufficient statistics over the next few years. By comparing luminosity functions at redshift 6, 8, 10, and 12, astronomers will track how the galaxy population evolved during the reionization epoch. Changes in the luminosity function reveal when different mass galaxies dominated star formation. If the faint end steepens at higher redshift, it indicates that dwarfs became increasingly important earlier in cosmic history. If the bright end grows, it suggests that massive galaxies assembled earlier than models predict. Either result constrains galaxy formation models. The luminosity function is one of the most fundamental observables in extragalactic astronomy. Reproducing its shape and evolution is a key test of theoretical models. Galaxy GLZRR10 at redshift 10.1 shows strong Lyman alpha emission, unusual for such high redshift. Lyman alpha photons are easily absorbed by neutral hydrogen. During reionization, most of the universe's hydrogen was neutral, blocking Lyman alpha from escaping galaxies. Detecting Lyman alpha at redshift 10 suggests that the galaxy sits in an ionized bubble. Star formation and AGN activity within the galaxy and its neighbors have ionized surrounding hydrogen, creating a transparent region through which Lyman alpha can escape. These ionized bubbles gradually merged and grew during reionization. By redshift 6, the bubbles overlapped, completing reionization. At redshift 10, the process was still underway, with isolated bubbles scattered through mostly neutral space. The size of the bubble around GLZRR10 can be estimated from the Lyman alpha emission properties. Detailed modeling suggests a bubble radius of a few million light-year, large enough to contain multiple galaxies. This indicates that GLZRR10 is not isolated, but part of a small group or protocluster. Group environments at high redshift are rare in simulations. Most galaxies form in isolated halos, with mergers occurring gradually over time. Finding evidence for groups at redshift 10 suggests that some regions of the early universe were already overdense, collapsing faster than average. These overdense regions are the seeds of galaxy clusters. By tracking which high redshift galaxies reside in groups, astronomers can predict where clusters will form. Future observations at lower redshifts can then confirm whether those regions indeed became clusters. This connection between high redshift groups and present-day clusters provides a powerful test of cosmological structure formation. The seeds observed at redshift 10 should grow into the massive clusters observed at redshift 0. Verifying this continuity validates the hierarchical assembly picture. Galaxy Cleos 9 at redshift 9.8 appears exceptionally blue, indicating minimal dust content. Dust absorbs ultraviolet light and re-emits it in the infrared, reddening a galaxy's appearance. The lack of dust in Cleos 9 suggests that either dust has not yet formed or it has been destroyed by intense radiation. Dust forms in the atmospheres of evolved stars and in supernova HHOs. Young galaxies have had less time for these processes to operate, resulting in lower dust content. But even modest star formation over tens of millions of years should produce some dust. The extreme blueness of Cleos 9 implies either very young age, less than 50 million years of star formation, or efficient dust destruction. Intense ultraviolet radiation from massive stars can heat dust grains to the point where they sublime into gas, removing them from the interstellar medium. Alternatively, Cleos 9 might have recently experienced a burst of star formation that has not yet produced significant dust. The stars currently visible are young and hot, emitting primarily ultraviolet light. Over the next 100 million years, these stars will evolve, some will die, and dust will accumulate. This evolutionary sequence is predicted by models, but observing it in action provides confirmation. Webb can track how dust content changes with galaxy age and star formation history by measuring dust in galaxies across a range of redshifts and stellar ages. Initial results show that dust increases with time, as expected. Galaxies at redshift 6 have more dust than those at redshift 10. Within a given redshift, older galaxies have more dust than younger ones. The trends match model predictions. But the scatter is large. Some galaxies have much more or much less dust than their age, and redshift would predict. This scatter reflects diversity in star formation histories, supernova rates, gas content, and environmental factors. Understanding this scatter requires larger samples. With hundreds of galaxies spanning a range of properties, astronomers can isolate which factors most strongly influence dust content. Is it total stellar mass, star formation rate, metallicity, environment, or some combination? Answering these questions builds a complete picture of galaxy evolution. Dust plays important roles in star formation, obscuring ultraviolet light and regulating gas temperature. Knowing when and how dust accumulates informs models of these processes. The galaxies Webb observes at redshift 10 and beyond are the ancestors of every galaxy in the present-day universe. The Milky Way's progenitors existed at those epochs, small dwarfs forming their first generations of stars. Over billions of years, those dwarfs merged and grew, eventually assembling into the spiral galaxy we inhabit. Tracing this lineage is one of astronomy's grand goals. From cosmic dawn to the present, following the assembly of structure across 13 billion years of evolution, Webb provides the high redshift endpoint. Surveys at intermediate redshifts fill in the sequence. Observations of the local universe show the final product. Connecting these pieces is challenging. Individual galaxies cannot be tracked across cosmic time. Instead, astronomers use statistics, comparing galaxy populations at different epochs and inferring evolutionary pathways from the differences. If massive galaxies at redshift 2 are more abundant than at redshift 10, mergers must have assembled smaller systems into larger ones. If star formation rates decline from redshift 2 to redshift 0, gas exhaustion or feedback must have quenched galaxies over time. These statistical arguments require large samples at each epoch. Webb is building the high redshift sample. Existing surveys provide intermediate and low redshift samples. Together, they enable statistical studies of galaxy evolution across cosmic time. The picture emerging shows a universe in continuous transformation. Galaxies at every epoch differ from those that came before and those that follow. Star formation rates rise and fall, morphologies change. Mergers rearrange stellar populations, black holes grow and impact their hosts. Through all this change, physical laws remain constant. Gravity, thermodynamics, quantum mechanics operate the same at every epoch. What changes is the conditions under which these laws operate. Density, temperature, chemical composition all evolve, leading to different outcomes from the same physics. Understanding this evolution is understanding the universe's history. Not as abstract cosmology, but as the lived experience of matter organizing itself into stars and galaxies. The story of how the universe built structure from simplicity is written in the Galaxies Webb observes. And that story is more complex, more rapid, more surprising than models predicted. The universe did not take its time. It did not proceed cautiously. Within a few 100 million years of the Big Bang, galaxies already filled space, stars already burned, black holes already grew. This urgency, this rapidity, this precocity is what makes the early universe so fascinating and so challenging to explain. Every observation reveals a cosmos more capable, more efficient, more organized than expected. The impossible galaxies are just the most extreme examples of a broader pattern. That pattern is what science is now working to explain. And the explanation, when it comes, will deepen our understanding of how the universe works. Not just in the early epochs, but across all of cosmic time. Because the processes operating at redshift 10 are the same processes operating today, just under different conditions. Webb is revealing those processes in action. The data is accumulating, the models are improving, and slowly, understanding is emerging. Not complete understanding, not final understanding, but progress toward a coherent picture of how galaxies actually form. This is the reality James Webb reveals, and it is magnificent. The JWST Extragalactic Medium Band Survey, GEMS, takes a different approach from broadband imaging. Instead of using a few wide filters that collect lots of light, GEMS employs narrow filters targeting specific emission lines. This allows mapping of ionized gas in early galaxies with spatial resolution. Hydrogen emission traces active star formation. Oxygen emission reveals metal-enriched regions. By comparing different emission lines across a galaxy's extent, astronomers map where stars form, where metals concentrate, where ionized bubbles exist. Early results from GEMS show that star formation in high redshift galaxies is often clumpy rather than smooth. Instead of uniform disk-wide star formation, activity concentrates in knots and clumps scattered throughout the galaxy. These clumps might be giant molecular cloud complexes, each containing millions of solar masses of gas forming stars at high rates. The clumpiness has implications for galaxy evolution. If star formation is concentrated in clumps, feedback from those clumps affects the surrounding galaxy differently than distributed star formation would. Supernovae from one clump might blow out gas in that region while leaving others unaffected. Over time, the clumps might migrate toward the galaxy center due to dynamical friction, eventually coalescing into a central bulge. This migration could help explain how disk galaxies develop bulges without requiring major mergers. Testing this scenario requires tracking clump properties across cosmic time. Do high redshift galaxies have more and larger clumps than lower redshift galaxies? Do the clumps fade as galaxies age? Do they migrate as predicted? Webb's resolution and sensitivity enable these studies. Previous telescopes could barely resolve early galaxies as extended objects, let alone map internal structure. Webb sees details within galaxies, revealing the spatial distribution of star formation and stellar populations. One target, galaxy ALESS 731 at redshift 8.6, shows 3 distinct clumps each forming stars at 10 to 20 solar masses per year. The clumps are separated by several thousand light-year, embedded in a diffuse stellar halo. The morphology suggests recent merger activity, with the clumps representing the remnants of smaller galaxies now coalescing. If this interpretation is correct, ALESS 731 is caught in the act of hierarchical assembly. The snapshot shows how smaller systems merge to build larger galaxies. Over the next few 100 million years, the clumps will spiral inward and merge into a single core, creating a more concentrated galaxy. This process should be common at high redshift. Dark matter simulations predict that halos merge frequently, bringing their galaxies together. But observing mergers in progress is difficult because they happen quickly on cosmic timescales. A merger might take only 100 million years from first contact to final coalescence. At any given moment, only a small fraction of galaxies are actively merging. Detecting this fraction requires large samples. Webb surveys eventually will image thousands of high redshift galaxies, enabling statistical measurements of merger rates. Preliminary estimates suggest that roughly 10 to 20% of massive galaxies at redshift 8 show morphological signs of recent mergers. This fraction is higher than at redshift 0, where only a few percent of massive galaxies appear to be merging. The increase matches theoretical predictions that mergers were more common in the denser early universe. But connecting morphological disturbances to actual mergers requires care. Not all irregular galaxies are merging. Some might be intrinsically chaotic due to intense star formation or gas-rich disks that have not yet settled into stable configurations. Kinematics provide additional evidence. If 2 velocity components appear in a galaxy's spectrum, it suggests 2 distinct systems, either merging or seen in projection. Follow-up integral field spectroscopy can map velocity across the galaxy's extent, revealing the motion of different components. Webb's NIRSPEC instrument includes an integral field unit capable of these observations. The field of view is small, only a few arcseconds, but sufficient to map kinematics in compact high redshift galaxies. Early programs are beginning to obtain such data, building samples of kinematically resolved early galaxies. Results show a mix of ordered rotation and chaotic motion. Some galaxies exhibit clear velocity gradients consistent with rotating disks. Others show complex kinematics with multiple velocity components, suggesting either mergers or turbulent gas motion. Distinguishing between these scenarios often requires detailed modeling. Simulations of mergers predict specific kinematic signatures, depending on the merger geometry and mass ratio. Turbulent disks produce different patterns, with random velocities superimposed on ordered rotation. Comparing observed kinematics to simulated predictions helps classify individual galaxies. This classification then feeds into statistical studies of how common different evolutionary pathways were at each epoch. The Cosmic Evolution Early Release Science Survey, CERS, imaged a strip of sky roughly 10 arc-minutes long. This field contains thousands of galaxies across a wide range of redshifts. The survey was designed as an early release science program to test Webb's capabilities and provide data to the community quickly. CERS data has already produced numerous discoveries. Multiple papers report record-distance galaxy candidates, early quasars, rare galaxy types, unexpected spectroscopic features. The richness of the dataset demonstrates Webb's power to find diverse objects across cosmic history. One particularly interesting CERS object is a galaxy at redshift 9.1, showing strong polycyclic aromatic hydrocarbon emission. PAR molecules are complex carbon-based molecules that form in the interstellar medium of star-forming galaxies. They emit strongly in mid-infrared wavelengths when excited by ultraviolet radiation. Detecting PARs at redshift 9 is surprising, because PAR formation requires carbon and other heavy elements. The galaxy must be chemically enriched to produce PARs. This suggests rapid chemical evolution, consistent with the high metallicities observed in some early galaxies. PAR emission also indicates the presence of dust, since PARs are associated with dusty regions. But the dust content inferred from PARs is lower than in comparable local galaxies. Early galaxies seem to have PAHs without as much dust, possibly because dust is still accumulating. Understanding PAR evolution provides another window into how the interstellar medium of galaxies changes over time. From the first chemically pristine environments to the dust and molecule-rich environments of modern galaxies, the progression reflects billions of years of stellar processing. Webb's mid-infrared spectrograph can detect PAR features across cosmic time. By measuring PAR strength in galaxies at different redshifts, astronomers trace when these molecules became abundant. The timeline of PAA emergence constrains models of chemical evolution and dust formation. The SMACS J723 3 to 7,327 cluster, site of Webb's first deep field, contains hundreds of galaxies at redshifts from 0.4 to beyond 10. The cluster's mass lenses background galaxies, creating arcs and multiple images. Webb's first deep field image showed this lensing in exquisite detail, revealing the power of combined gravitational telescopes. Follow-up spectroscopy identified redshifts for many of the lensed galaxies. One spectacular arc corresponds to a galaxy at redshift 6.2, stretched into a nearly complete Einstein ring by the cluster's gravity. The magnification factor exceeds 30, allowing detailed study of a galaxy that would otherwise be too faint. Analysis of this lensed galaxy reveals an edge-on disk with a central bar. The morphology is surprisingly mature for redshift 6.2. Bars typically form in stable disk galaxies after several orbital times, requiring hundreds of millions of years. Finding a barred galaxy when the universe was less than 1 billion years old challenges formation timescales. The bar might have formed through gravitational instabilities in a gas-rich disk. In high gas fraction environments, bars can form quickly through self-gravity. Alternatively, a minor merger could have triggered bar formation through tidal forces. Regardless of the formation mechanism, the existence of bars at high redshift indicates that disk galaxies achieved stability and organization earlier than expected. This aligns with the broader theme of accelerated structure formation that Webb continues to uncover. Another lensed galaxy in the SMACS field shows a spectacular tidal tail, a stream of stars pulled out by gravitational interaction with a neighbor. The tail stretches for tens of thousands of light-years, containing millions of stars stripped from the galaxy's outer regions. Tidal tails are common in merging galaxies. As two galaxies interact, tidal forces pull stars and gas into extended streams. These tails can persist for hundreds of millions of years after the merger completes, gradually dispersing into the intergalactic medium. Finding tidal features at high redshift confirms that mergers and interactions were shaping galaxies in the early universe. The features provide direct visual evidence of hierarchical assembly in action. The Next Generation Deep Extragalactic Exploratory Public Survey (NGD-PEP) aims to image the same patch of sky repeatedly over multiple years, building up extraordinary depth. Each new observation adds to the total integration time, pushing fainter and fainter. The ultimate goal is to detect galaxies at redshift 15 or beyond. If such galaxies exist, they represent the absolute earliest epoch of star formation, less than 250 million years after the Big Bang. Finding them would reveal when the first stars actually ignited. If no galaxies appear at redshift 15 despite deep observations, that also constrains models. A lack of galaxies implies that star formation had not yet begun or was so inefficient that galaxies remained below detection thresholds. Either outcome teaches something about cosmic dawn. NG-deep observations are ongoing. The survey accumulates depth gradually as additional visits occur. Final sensitivity will take years to achieve. But early data already pushes beyond previous limits, hinting at possible detections at redshift 13 and 14. These candidates await spectroscopic confirmation. Distinguishing true high redshift galaxies from foreground contaminants requires spectroscopy. But at the faint levels NG-deep reaches, even Webb struggles to obtain spectra. Integration times of many hours might be needed for each target. The trade-off between depth and spectroscopic confirmability is a perpetual challenge in extragalactic astronomy. Surveys can always image fainter objects than spectroscopy can confirm. This creates populations of photometric candidates at the highest redshifts, some fraction of which are real and others are contaminants. Over time, deeper spectroscopy and improved instrumentation will confirm more candidates. But there will always be a frontier where imaging outpaces spectroscopy. Learning to work with probabilistic redshifts and statistical samples becomes necessary. The panoramic survey combines Webb imaging with ground-based spectroscopy from the Keck telescope. By coordinating observations, the survey efficiently identifies candidates with Webb and confirms them with Keck's larger collecting area. The synergy between space and ground facilities optimizes the science return. Keck's 10-meter mirror can collect more light than Webb's 6.5-meter mirror, making it better for spectroscopy of bright targets. But Keck operates from the ground, limiting its infrared sensitivity due to atmospheric emission. Webb operates in space, avoiding atmospheric interference, but with a smaller mirror. Each facility has strengths. Using them together maximizes efficiency. Webb finds the candidates. Keck confirms the bright ones. Webb follows up on faint targets that Keck cannot reach. The division of labor advances science faster than either facility alone. Other ground-based telescopes contribute as well. The Very Large Telescope in Chile, the Gemini telescopes in Chile and Hawaii, the Subaru telescope in Hawaii. All conduct observations coordinated with Webb programs. These collaborations represent the future of astronomy. No single facility can do everything. Space telescopes, ground telescopes, radio arrays, neutrino detectors, gravitational wave observatories. Each provides unique capabilities. The most powerful science comes from combining them. Webb's discoveries of massive early galaxies have motivated theorists to revisit fundamental assumptions. One area of focus is the initial conditions from inflation. Different inflation models predict different amplitudes of density fluctuations on small scales. If small-scale fluctuations are larger than standard predictions, structure formation accelerates. Regions with higher density collapse earlier, forming stars and galaxies sooner. This could help explain why galaxies assembled so quickly. Testing this requires comparing the observed distribution of galaxies with predictions from different inflation models. The clustering strength, the abundances at different masses, the redshift evolution of the population, all contain information about the initial fluctuations. Preliminary analyses suggest that standard inflation models struggle to match Webb's observations. The most massive galaxies at the highest redshifts appear too abundant. Either the models need adjustment or some other factor is at play. One possibility is that galaxy formation efficiency varied more than models assume. Perhaps some halos converted gas into stars far more efficiently than average. If these highly efficient halos were rare but not impossibly so, they could account for the massive early galaxies without requiring exotic initial conditions. Identifying what makes a halo efficient at forming stars is an active research area. Halo mass matters. More massive halos have deeper potential wells that retain gas better against feedback. But mass alone does not determine efficiency. Halo spin affects efficiency. Rapidly rotating halos might form stars more efficiently by concentrating gas into dense disks. Slowly rotating halos might allow gas to settle more gradually. Halo concentration matters too. Halos with steep density profiles concentrate mass in their centers, increasing gravitational forces and accelerating gas collapse. Halos with shallow profiles spread mass over larger volumes, slowing collapse. Environment plays a role. Halos in overdense regions experience more frequent interactions and mergers, affecting their star formation histories. Isolated halos evolve differently than halos in groups or protoclusters. Chemical composition influences star formation. Gas with even trace amounts of heavy elements can cool more efficiently than pristine hydrogen and helium. This affects fragmentation and the characteristic mass of forming stars. All these factors combine to produce the diversity of galaxies Webb observes. Understanding which factors dominate requires comparing observations to simulations that include realistic physics. Modern simulations are increasingly sophisticated. They track dark matter gravity, gas thermodynamics, star formation, supernovae feedback, black hole growth, black hole feedback, magnetic fields, cosmic ray pressure, radiation transfer. Each added process makes simulations more realistic, but also more computationally expensive. The largest simulations model cubic regions, hundreds of millions of light-year on a side, containing millions of galaxies. These simulations reproduce the large-scale structure of the universe, but with limited resolution on individual galaxies. Smaller zoom simulations focus on single galaxies or small groups, modeling them with high resolution. These capture details of star formation and feedback, but miss the large-scale environment. Comparing Webb observations to both types of simulations provides complementary constraints. Large-scale simulations predict galaxy abundances and clustering. Zoom simulations predict internal structure and star formation histories. Matching both sets of predictions to observations tightly constrains models. The current status is that simulations match some observations well, but struggle with others. The overall galaxy population at intermediate redshifts is reproduced reasonably. But the high redshift massive galaxies remain problematic. Even the most optimistic simulations underproduce them. This tension drives simulation development. New prescriptions for star formation, updated feedback recipes, alternative dark matter scenarios. Each is tested against the growing body of Webb data. The ultimate goal is a simulation that matches all observations from redshift 10 to redshift 0. Such a simulation would constitute a comprehensive model of galaxy evolution, one that could make predictions for future observations with confidence. We are not there yet, but progress is steady. Each new piece of observational data informs the next generation of simulations. Each simulation that fails teaches something about what physics matters. The iterative cycle continues. One exotic proposal suggests that some early galaxies might host primordial black holes formed in the first seconds after the Big Bang. These hypothetical objects would differ from black holes formed from stars or direct collapse. They could have any mass, from microscopic to thousands of solar masses. If primordial black holes exist and reside in early galaxy halos, they could affect structure formation. Halos containing primordial black holes might collapse earlier due to the concentrated mass. The black holes might also seed the formation of supermassive black holes more efficiently than stellar mass seeds. Evidence for primordial black holes remains weak. No definitive detection has occurred. The idea remains speculative, but Webb's observations of early galaxies provide new ways to search. If early galaxies systematically contain more massive black holes than formation models allow, primordial black holes become a possible explanation. Measuring black hole masses at high redshift tests this scenario. Current data shows that early supermassive black holes are more massive than expected, but not impossibly so. Rapid growth from stellar seeds remains plausible. Primordial black holes are not required, though they are not ruled out either. As the sample of early black holes grows, the constraints will tighten. If essentially every early galaxy contains a black hole too massive to have grown from stellar seeds, exotic mechanisms become necessary. If most are consistent with stellar seed growth, primordial black holes fade as an explanation. The metallicity evolution of galaxies provides another probe of early star formation. Each generation of stars enriches the interstellar medium with heavy elements. By measuring metallicity as a function of time, astronomers reconstruct the chemical enrichment history. Webb measures metallicity through emission line ratios. Strong lines like oxygen 3 and hydrogen beta allow rough metallicity estimates, even with modest signal to noise. More precise measurements require additional lines and careful modeling. The data shows that metallicity increases from redshift 10 to redshift 0, as expected. But the rate of increase varies between galaxies. Some enrich rapidly, reaching 30% solar metallicity by redshift 8. Others remain metal poor, with metallicities below 10% solar at the same epoch. This scatter reflects different star formation histories. Galaxies that formed stars vigorously early enriched quickly. Galaxies that formed stars more gradually enriched slowly. The diversity in enrichment tracks the diversity in assembly histories. Metallicity also correlates with stellar mass. More massive galaxies tend to be more metal-rich at any given redshift. This mass-metallicity relation appears at all epochs where measurements exist, from redshift 0 to redshift 8. The existence of a mass-metallicity relation at high redshift indicates that the processes establishing it operate early. Massive galaxies either formed stars earlier, allowing more time for enrichment, or formed stars more efficiently, producing more metals per unit time. Outflows complicate the interpretation. If low-mass galaxies experience more efficient outflows than massive galaxies, they could preferentially lose metals to the intergalactic medium. This would lower their measured metallicity independent of their star formation history. Distinguishing between these scenarios requires measuring outflow rates. Spectroscopic signatures of outflowing gas, such as blue-shifted absorption lines, indicate mass loss. The strength and extent of these signatures constrain outflow rates. Webb can detect outflow signatures in bright galaxies with sufficient integration time. As the data accumulates, outflow measurements will improve, revealing how efficiently galaxies retained their metals versus losing them to outflows. The circumgalactic medium, the diffuse gas surrounding galaxies, harbors clues about inflows and outflows. Gas flowing into galaxies from the cosmic web enriches the circumgalactic medium. Gas expelled by feedback adds to it as well. Studying the circumgalactic medium at high redshift is challenging because the gas is faint and extended. Absorption line studies using background quasars provide the main probe. When a quasar's light passes through a foreground galaxy's circumgalactic medium, absorption features appear in the quasar spectrum. The strength and width of these features reveal the density, temperature, and velocity of the circumgalactic gas. By observing many quasar sightlines passing near galaxies at different distances, astronomers map the evolution of the circumgalactic medium. Webb contributes by identifying more high redshift galaxies near quasar sightlines. Combined with ground-based spectroscopy of the quasars, this enables circumgalactic medium studies at earlier epochs than previously possible. Preliminary results suggest that the circumgalactic medium at high redshift is metal-enriched, indicating that early galaxies expelled significant amounts of processed gas. This enriched gas might eventually rain back onto the galaxies, contributing to later star formation. The cycle of gas flowing in, forming stars, being expelled by feedback, and falling back in is fundamental to galaxy evolution. Understanding this cycle requires measuring inflow rates, outflow rates, and the metallicity of both components. Webb measures the star-forming galaxies themselves. Ground-based telescopes measure the circumgalactic absorption. Together, they constrain the cycle. Over time, a complete picture of gas flows in the early universe will emerge. The cosmic star formation history describes how the universe's total star formation rate evolved over time. Summing up the star formation in all galaxies at each epoch produces this history. It rises from near zero at cosmic dawn, peaks around redshift 2, and declines to the present day. Webb's observations are refining the early part of this history. By measuring star formation rates in galaxies at redshift 10 and beyond, astronomers constrain when the rise began and how steep it was. Current data suggests that star formation ramped up quickly between redshift 15 and redshift 8. By redshift 8, the universe was forming stars at a substantial fraction of the peak rate. This rapid rise indicates that galaxy assembly proceeded quickly. The shape of the star formation history reflects the balance between gas supply, star formation efficiency, and feedback. Early on, abundant gas and increasing halo masses drove increasing star formation. Later, gas exhaustion and more effective feedback slowed the rate. Understanding the physical drivers of the star formation history requires detailed modeling. Simulations that reproduce the observed shape must get the gas physics, star formation, and feedback approximately right. Simulations that fail to match the observations are missing key processes. Webb's contribution to refining the high redshift star formation history will improve simulations. Better constraints on the early rise inform models of when galaxies turned on. This feeds back into understanding reionization, chemical enrichment, and the buildup of stellar mass. Every piece of the cosmic puzzle connects to others. Galaxy formation affects reionization. Reionization affects subsequent galaxy formation by heating the intergalactic medium. Chemical enrichment enables more efficient star formation. Star formation produces feedback that regulates further enrichment. The web of connections means that understanding one aspect requires understanding many. Webb provides observational anchors at high redshift. Simulations provide the framework connecting different epochs and processes. Together, they build toward comprehensive models of cosmic evolution. The galaxies Webb discovers are not just interesting in themselves. They are probes of fundamental physics, windows into cosmic dawn, clues about how the universe assembled structure. Each measurement constrains models. Each new galaxy adds to the statistical sample. Each surprise motivates theoretical development. This is how science advances. Observations push theory. Theory motivates new observations. The cycle spirals upward, each iteration climbing closer to truth. Webb has accelerated this cycle dramatically, providing observations decades ahead of when they were expected. The result is a golden age of extragalactic astronomy. More data, better data, stranger data than ever before. Theorists racing to keep up. Observers racing to exploit the new capabilities. The entire field energized by discovery. And the discoveries continue. Every new observing program finds something unexpected. Every deep field reveals record distance candidates. Every spectroscopic campaign confirms galaxies that should not exist. The universe, it seems, delights in surprising us. And James Webb is the instrument revealing just how surprising it can be. The Nancy Grace Roman Space Telescope will launch in the late 2022, complementing Webb with a wider field of view. Where Webb excels at deep pointed observations, Roman will excel at surveying large areas. Together, they will map the early universe with unprecedented completeness. Roman's field of view is 100 times larger than Webb's near-infrared camera. This allows surveys covering degrees of sky rather than arc minutes. Such wide surveys will find rare objects that occupy small fractions of the sky. Extremely massive early galaxies, unusual quasars, strong gravitational lenses. The combination of Webb's depth and Roman's area provides optimal discovery power. Roman identifies interesting regions and individual targets. Webb follows up with detailed observations. The synergy between wide and deep maximizes scientific return. Planning for Roman observing programs is already underway. Astronomers are designing surveys to complement Webb rather than duplicate its observations. Different areas of sky, different strategies, different science goals. Together, the two missions will transform our understanding of cosmic dawn. Ground-based extremely large telescopes will also contribute. The Extremely Large Telescope in Chile, with its 39-meter mirror, will achieve resolution higher than Webb for bright targets. High-resolution spectroscopy of early galaxies will resolve velocity structures, map ionized regions, detect multiple kinematic components. The Giant Magellan Telescope and the 30-meter telescope add to the capabilities. Each has unique strengths in wavelength coverage, instrumentation, or location. Together with Webb and Roman, they form an unprecedented suite of facilities. This multi-facility approach is necessary because the questions are complex. No single telescope can answer everything. Depth, area, resolution, wavelength coverage, spectroscopic capability. Different science goals require different combinations. The era of single telescope science is ending. The future belongs to coordinated campaigns using multiple facilities. Large collaborations spanning institutions and nations, all working toward common goals. Webb has inaugurated this era. The telescope's discoveries are so rich, so surprising, so numerous, that follow-up demands exceed any one facility's capacity. Prioritization becomes essential. Which targets merit deep spectroscopy? Which merit wide-area imaging? Which merit high-resolution follow-up? These decisions shape the direction of research. Limited telescope time forces choices. The community must agree on priorities, balancing individual interests with collective goals. The process is messy but productive. Debate, discussion, proposal pressure, peer review. From this emerges consensus on what matters most. The highest priority targets receive the most resources. Novel ideas get chances to prove themselves. The field advances through collective effort. James Webb's discoveries of impossible galaxies have ignited intense activity. Dozens of theoretical papers propose explanations. Hundreds of follow-up observations are planned or underway. Thousands of astronomers are engaged with the data, analyzing images, extracting spectra, measuring properties. This level of activity reflects the significance of the discoveries. When observations challenge fundamental understanding, the response is massive. Resources flow toward the problem. Talent concentrates on finding solutions. Progress accelerates. The impossible galaxies will eventually become understood galaxies. The mystery will resolve. Models will match observations. The tension will ease. But that resolution might take years or even decades. In the meantime, the search for answers drives innovation. New simulation techniques are developed to handle the physics better. New observational strategies are designed to constrain key parameters. New theoretical frameworks emerge to explain the data. This is science at its best, driven by data, constrained by observations, tested against reality. Not abstract speculation, but concrete engagement with what the universe actually is. And what the universe actually is turns out to be more impressive than imagined. More capable of rapid structure formation, more efficient at converting gas into stars, more organized, even at early times. These are not failures of science but successes of observation revealing reality. The philosophical implications are profound. We exist because the early universe formed galaxies efficiently. Those galaxies produced heavy elements. Those elements eventually assembled into planets and life. If galaxy formation had been slower, if star formation had been less efficient, if structures had taken longer to emerge, the timeline to life might have been delayed. Whether life elsewhere in the universe faced similar timelines or different ones remains unknown. But Webb's observations show that our cosmic environment formed quickly. The The Milky Way's ancestors were building stars when the universe was less than 3% of its current age. This means the building blocks of life appeared early: carbon, oxygen, nitrogen, iron, all produced in early galaxies and dispersed through supernovae and stellar winds. By the time the Milky Way formed, the raw materials for planets and life were already present. Understanding the early universe is understanding our own deep history. The atoms in our bodies trace back to stars that formed billions of years ago. Some of those stars might have belonged to the early galaxies Webb observes. Our connection to cosmic dawn is direct and personal. This connection gives urgency to the research. Learning how galaxies formed is learning where we came from. The questions are not abstract. They touch the foundations of existence. James Webb provides the means to answer these questions. The telescope reveals the early universe directly, not through inference or extrapolation, but through observation. Real galaxies, measured and catalogued. Their properties constrain models. Their existence proves that rapid assembly occurred. The next generation of astronomers will build on Webb's foundations. Students today are analyzing Webb data for their theses. The lessons they learn, the skills they develop, the insights they gain will shape research for decades. These future astronomers will have tools beyond Webb: larger telescopes, better detectors, faster computers, smarter algorithms. But they will always look back at Webb as the mission that opened the high redshift universe, just as previous generations looked back at Hubble as the mission that revealed galaxy diversity and cosmic expansion acceleration. Just as earlier generations looked back at ground-based surveys that first mapped large-scale structure, each generation builds on what came before. Webb's contribution is revealing cosmic dawn, showing when and how the first galaxies assembled. This knowledge joins the accumulated understanding passed down through decades of research. The impossible galaxies are part of that legacy. Objects that should not exist according to pre-Webb models, but do exist in reality. Their existence forces better models, drives theoretical innovation, expands our conception of what the early universe was capable of. In a broader sense, every unexpected discovery expands our conception of possibility. The universe continually demonstrates capabilities we had not imagined. Black holes exist. Gravitational waves propagate through space-time. Dark energy accelerates cosmic expansion, and now, massive galaxies assembled when the universe was barely born. Each surprise initially seems impossible. Each defies prior expectations. Yet each, upon investigation, turns out to follow physical law. The laws were always there. We simply had not understood their implications fully. This pattern suggests humility. Our models are approximations. Our understanding is incomplete. The universe operates according to principles we are still learning. Expecting it to conform to our current models is hubris. Better to approach with curiosity and openness. To observe carefully, measure precisely, and adjust understanding as needed. To follow the data wherever it leads, even when it challenges cherished ideas. James Webb embodies this approach. The telescope does not care what models predict. It observes what exists. And what exists, it turns out, is richer and stranger than models anticipated. The galaxies that should not exist are teaching humility to astrophysics. They demonstrate that despite decades of research, despite sophisticated simulations, despite careful theoretical work, the early universe still holds surprises. This is cause for excitement rather than disappointment. Surprises mean opportunities to learn. Each unexpected finding opens new research directions. The impossible galaxies have motivated papers, proposals, careers. Young researchers entering the field have a frontier to explore. The high redshift universe revealed by Webb offers questions for a generation. How did massive galaxies form so early? What made star formation so efficient? When did the first stars actually ignite? What role did black holes play? These questions will drive research for years. Answers will come gradually through accumulated observations and improved models. Understanding will deepen. The picture will clarify. But even as current mysteries resolve, new ones will emerge. Deeper observations will find galaxies at even higher redshifts. More detailed studies will reveal unexpected complexity. The frontier will shift but never disappear. This is the nature of science, a perpetual frontier, always advancing but never reached. Each answer raises new questions. Each discovery reveals new mysteries. The process continues as long as curious minds investigate. James Webb has pushed that frontier dramatically. The telescope revealed epochs and structures invisible to previous instruments. In doing so, it transformed our view of cosmic history from educated speculation to direct observation. The early universe is no longer a theoretical construct. It is an observed reality, captured in Webb's images and spectra. Those photons traveled across 13 billion years of expanding space to reach us. They carry information about conditions when the cosmos was young. Decoding that information is the work of this generation, extracting measurements, building models, testing hypotheses. The process is collaborative, involving thousands of people across many nations, all working toward shared understanding. The impossible galaxies are everyone's mystery. The data is public. Anyone with the skill and interest can analyze it. This open science model accelerates progress by engaging the broadest possible community. Students in developing nations can analyze the same data as professors at elite institutions. Amateur astronomers can discover interesting objects in survey images. Citizen science projects engage the public in classification tasks. This democratization of astronomy is one of Webb's legacies. The mission was funded publicly. The data belongs to everyone. The discoveries inspire globally. And the inspiration is real. Webb images appear in classrooms and museums worldwide. They spark conversations about the universe, about physics, about humanity's place in the cosmos. They make abstract cosmology concrete and visible. A child seeing a Webb image of distant galaxies might wonder what those galaxies are, how far away they are, whether they still exist. Those questions can lead to learning, to education, to careers in science. This pipeline of inspiration and education sustains the enterprise. Each generation of scientists was once children wondering about the universe. Webb plants those seeds of wonder in a new generation. The impossible galaxies, with their shocking properties and paradigm-challenging existence, are particularly effective at sparking curiosity. They seem impossible, yet exist. They defy expectations yet follow physical law. Reconciling these apparent contradictions requires understanding, and understanding requires learning. This is how science propagates. Through wonder, curiosity, learning, understanding, and then teaching the next generation. The cycle repeats, each iteration advancing knowledge. James Webb has given this cycle new fuel. The discoveries will be studied and debated for decades. Students will write dissertations on Webb data. Textbooks will revise chapters on early galaxies. The mission's impact extends far beyond its operational lifetime. Even after Webb stops observing, the data will remain valuable. Future instruments will provide new observations to compare. New theoretical insights will offer fresh interpretations. The archive will continue to yield discoveries long after the mission ends. This longevity of impact is what defines great observatories. Not just the immediate discoveries, but the lasting contributions to knowledge. Webb has secured its place through the impossible galaxies and countless other findings. The universe Webb reveals is magnificent, vast, ancient, dynamic, complex. Filled with structures spanning scales from planets to superclusters. Governed by physical laws operating across 13.8 billion years of evolution. And at the root of all this magnificence are the processes operating in the early universe. The formation of the first stars, the assembly of the first galaxies, the ionization of hydrogen, the enrichment of pristine gas with heavy elements. These processes set the stage for everything that followed. Without early star formation, no heavy elements. Without heavy elements, no rocky planets. Without planets, no life. The chain of causation runs from cosmic dawn to the present. Understanding that chain means understanding our origins at the deepest level. Not just biological evolution or planetary formation, but the cosmic processes that made those possible. The full story of how we came to exist reaches back to the first galaxies. James Webb is revealing that part of the story. The chapters covering cosmic dawn, first light, early assembly. These chapters were speculative before Webb. Now they rest on observational foundations. The impossible galaxies are a major plot point in this story. They demonstrate that the early universe was more dynamic than expected. Structure emerged faster. Stars formed more efficiently. Complexity appeared sooner. This accelerated timeline has implications for the likelihood of life. If galaxies and stars formed quickly throughout the universe, planets, and potentially life, had more time to develop. The window for biological evolution lengthens if cosmic evolution proceeds rapidly. Whether this makes life more common or not depends on other factors. But it shifts the timeline, providing more opportunities across cosmic history. These questions extend beyond astrophysics into astrobiology and philosophy. What does rapid structure formation imply for cosmic habitability? If massive galaxies assembled early, did they produce rocky planets early? Did life emerge early in cosmic history? We may never know with certainty, but Webb's observations constrain the possibilities. They show that the building blocks were in place early. What happened afterward remains to be determined. The search for biosignatures on exoplanets is another of Webb's missions. The telescope can analyze the atmospheres of planets orbiting nearby stars, searching for chemical signatures that might indicate life. These searches connect to the study of early galaxies. The same telescope reveals both cosmic dawn and potentially cosmic life. Both represent fundamental questions about existence. Both push the boundaries of knowledge. And both demonstrate that we live in an age of extraordinary capability. Humanity has built instruments that observe the universe's earliest moments and search for life beyond Earth. Technologies that seemed like science fiction decades ago are now operational. This capability comes with responsibility. To use these tools wisely, to pursue knowledge for its own sake and for the benefit of all, to share discoveries openly, to inspire the next generation. James Webb fulfills these responsibilities. The mission operates transparently. The data is public. The discoveries are shared globally. The science is conducted ethically and collaboratively. This is the model for modern astronomy. Large missions funded publicly, operated professionally, serving humanity's quest to understand the cosmos. The impossible galaxies exemplify what this model achieves. Discoveries that challenge understanding, expand knowledge, inspire wonder. Results that could only come from major investments in capability and from talented people working together toward common goals. Looking forward, the next decades will see Webb's discoveries integrated into a comprehensive model of galaxy evolution. The tensions with theory will resolve as better models are developed. The impossible will become possible through deeper understanding. But that understanding will build on Webb's observational foundations. The galaxies the telescope discovered, the properties it measured, the surprises it revealed, all will remain as facts requiring explanation. Future theories must accommodate these facts. Models that fail to produce massive galaxies at high redshift will be discarded. Simulations that cannot match the observed abundances will be revised. The data constrains, channels, guides theoretical development. This is how observational astronomy drives progress. By revealing what actually exists, it forces theory to match reality rather than speculation. And reality, as James Webb shows us, is more extraordinary than our models predicted. Galaxies appeared earlier, grew faster, organized sooner. The early universe was vigorous and capable in ways we had not fully appreciated. This vigor, this capability, this propensity for creating structure from chaos is fundamental to the universe's nature. Matter organizes itself, given the opportunity. Gravity pulls, thermodynamics governs, quantum mechanics enables. From these processes emerge stars, galaxies, planets, life, consciousness. We are the universe observing itself. Matter arranged in configurations that permit awareness, curiosity, investigation. The atoms in our bodies were forged in stars. The structures in our brains reflect billions of years of evolution. Our thoughts engage with questions spanning cosmic history. James Webb is a tool this self-aware universe built to examine its own past. Through Webb, the universe looks back at its infancy, observes how it began, measures how it evolved. The impossible galaxies are what the universe reveals to itself through this examination. Structures that formed when everything was new. Systems that assembled with surprising speed and efficiency. Ancestors of every galaxy in the modern cosmos. These galaxies existed before the Sun, before the Earth, before life. Their light has traveled across billions of years to reach Webb's detectors. And from that light, we extract knowledge about cosmic dawn. This is humanity's gift to the universe, the capacity to understand, to measure, to know. We turn photons into data, data into knowledge, knowledge into understanding. We decode the universe's history and share it with anyone willing to listen. The impossible galaxies are part of that history. They teach us that the universe is more than we imagined, richer, stranger, more dynamic. They teach humility about how much we have yet to learn. They teach wonder at what the cosmos can accomplish. And they teach optimism about what we might discover next. If Webb's first years revealed galaxies that should not exist, what might the next years reveal? What other surprises wait in the data? What other impossibilities will become observations? The universe has proven generous with surprises. James Webb has proven capable of finding them. The combination promises a decade of discovery, revelation, and advancing knowledge. This is the gift we give ourselves through investments in science. The capability to observe, understand, and marvel. The impossible galaxies justified the entire Webb mission through what they teach about cosmic dawn. But they are only the beginning. Webb continues observing, continues discovering, continues revealing. Each new dataset brings potential breakthroughs. Each observation refines our understanding. The journey is far from over. The impossible galaxies opened a chapter. Many pages remain to be written, and James Webb holds the pen, inscribing observations that future generations will study, interpret, and build upon. We are privileged to witness this process. To live in an era when the early universe comes into focus, when impossible becomes observable. When surprise becomes routine because the universe itself is so endlessly surprising. This is what James Webb has given us. Not just data or images, but a deeper appreciation for the cosmos we inhabit. A universe more remarkable than we knew, more dynamic in its youth, more efficient at building structure, more generous with opportunities to learn. The galaxies that should not exist, exist. They shine across billions of light-years, their ancient light finally reaching us. And in that light, we read the story of cosmic dawn. A story more amazing than fiction, more complex than models predicted, more real than any speculation. That is the power of observation. To reveal truth regardless of expectations. To show what is rather than what we thought should be. James Webb wields that power with extraordinary capability, transforming our understanding of the universe, one impossible galaxy at a time.